So, and you can go deeper. You can fine. Come back in the things. One thing is this. First thing is one beyond money execution. We do have a nice process. If I take 3 minutes, like 5 minutes, man, support you very important to you. And first of all, you can organize just all organizers, especially when you know what for actually such twice in dealing. Very happy to present my work. So, today we talking about broadly, uh, but mainly I'll be touching upon my skin tone here, recent business. That now, maybe need to beat in other ways up because most of those, energy so maybe myself for should be so these are the parameters along which I am moving in my job. So we're definitely starting with the basic ideas of items and tracking mechanism on it. Which is the essence of honor simulation, which is the creations in this system. And then some special localized explanations which are very much useful for technology. I mean, then applications to quantum technology science. The nature of those. Well, one of us know from the basis of statistical mechanics that temperature and so the randomly moving in the system, they react like quantum particles. But then as you go to temperature, they evolve with barometer. When it was temperature, these different movement is making each other. So that's the point where these particles is actually quantum vision. And then they create instead of separate, they create a cloud. It is actually what is the information. So it took long time to experiment. We want to store the experiments. So for finding the exact system which can actually relocating a temperature, and at the same time being in dynamic state, then also there should be some cooling method which can take you to the another temperature. So these are the steps, which is the motivation of studies. First of all, you have to know that this is a simulation in already in China. This is a purely quantum machine. It's a highly tunable object, and that's the reason why which you reconcilize. And then this is a element of space not in Fourier space. So that's actually becomes a little bit disadvantage because you like to control it in the real space. Your fluids make it, in the external there to be only the real space. So use it not in well, since not get into this in quantizations, but directly one can go into this equation, which was also mentioned by a number of speakers in the same time. But when you look at this blue circle and red circle, where this is the non-linear data which arises from atom interactions, making two more interactions. This is external potential, which is finding the system. You can actually in experiments, in recent experiments, what is being done is you can actually have a this time. Then create a basic sequence, whichever. And then you bring it may be magnetic field, optical field both, and maybe any one of them to have an easy functional communication. So this is the way one can go ahead and apply such things, but definitely we need that have some information to forget, to have some information to analyze, you have to have the information which purpose. If it is renewable and also does not carry any information, you have to do a superposition of words to have enough questions. So the first thing which I just mention about solutions, which is also widely discussed, but then just the formation is that one has to balance the nonlinearity and dispersion mainly, but then you can the classification that things also can contribute. So what nonlinearity does when moving, the you move faster. So it means one can see the water the little breaks to the shoe. And then dispersion is the spreading of the wave. So this takes now can compensate exactly increase compensate exactly the calculator. And there are different forms of this kind of possibilities. So I'll be talking about that only. Which were not here. Let's model. So what we mentioned, the given we can actually address a couple of times in the same so recently, it's for but because learning language is very much used for technology, a lot of creative logic tricks and so on. I've done any interferometry actually. So this is the kind of study for one exact analytical methods. So now let us get into the quantum simulation, which I said, and which was actually predicted by basically these two points. He said that a better controllable system can be used when you are having difficulties or restrictions in academics or of subjects. So we have to have any situations where it is very tunable. So work like a simulator of previous one. So here in this case, what you do is optical entities. You can see the the counter optical lasers, the function of optical entities is known. This is a static wave generated by counter optical laser. If you put it in two sides, super lasers, so we have two the lattice. So this minimal is the near is true to these seven atoms. One division of it is in the original atoms. So this system can actually simulate the kind of a conventional situation, which is also non-linear, which is also having similar presentations. Well, here it is that a simple optical lattice is already studied, and that's the beginning of volume simulations and applications. If you superimpose optical lattice, is very simple. One is PDF, next to so you'll be getting this kind of thing. So this one is in this no straight down is between. So so what happens that you suppose in case this gas and this is called a period. So in optical language is the frequency. That's it. So it's a bichromatic because it's normal laser. So even it is said in the literature is a bichromatic like this, but definitely it's periodic. When you are going with that simple structure because it's routinely done in the experiment and you can predict the theory what it's supposed to do because it is used on theory limits. So yeah, so this position you can see that there are some intermediate minima which is not and also it is called geometrical infrastructures. The question is that can we do some advanced trap engineering on such kind of thing? We have actually this so look at this model. So we have next we can actually get from exactly that. And you can see that this science this T well corresponds to today like this. You will not look like this. So put together 3 periods. This blank space is 4 periods. Okay. So you can actually have multiple combinations of lattices, and then you can see that how many parameters. There are not parameters. What parameters can be used because lasers are very sophisticated. Amplitude can be tune, frequency can be tuned, everything can happen. So it can, using four static wave, can actually generate a different data structure. So some of just one gives that is a four elements. And you can see the growth lattice. Okay. So there are frustrated positions in between. Now, what is the essence of frustrated position in between that? You can separate the column. You have simple pyramid structure, you get the structure. Never will get analysis. Okay. Whether in brain. So you have to have a school that is no frustration in between. So that you can have a separation in how. This kind of but this is the, all these things are checked by stability analysis so that things are quite consistent in experiment with experimental parameter. Now, these are milliseconds which the cloud remains over. You can see that the deviation is the deviation from the initial density, which will that. And so this one is again that is this is for our application. Right. So the next one is trust engineering for estimating legal estimating. So it's new. Lots of new because this project when was theoretical now since now when it's statistical projects so that in 2013 this is clearly realized. It's 2013 later. And then we are given a theory and theory. And then it related whether because this temperature domain is completely unexplored, within temperature domain we can intuitively understand what is supposed to happen. Because if I ask you that if you this temperature, what should happen? You can immediately tell more or less. So this is the temperature is not understood here. So it is important that how this response to external like plan. So this is the idea that in a positive temperature, the requires increasing the temperature. So in this case, if you measure number of atoms, so it's a very similar situation. It's not like because it was studied laser because those are people I'm talking about yeah. And so that is what is very difficult to take. Because we are like living our lives, living our lives. This is the situation, positive temperature. If you go below critical temperature, the atoms are coming of the zero momentum because continuity is zero. But if you approach towards negative absolute temperature, what will happen? They will never come from zero momentum and they will have it will be at high. So this is some with experimental figures. This is the temperature which area this particular thing. These are laser intensities. Okay, entropy and this temperature. So this must critical damage. Ajay will be presenting in details. But here it is how we can go ahead with changing temperature. How do I know that if I want real temperature, what should I do? If I need real temperature, so temperature, what should I do? Or range, what should I do? So you see the trap profiles. This is a potential with the intensities. Yes. And then initially it is lattice and then it's possibility and then you have hyperbolicity, so on. So you can use any point here and accordingly you take the experimental value. And then this is the donut chart representation of one shell. So it's a number of atoms on its cell. So what it says is the number of atoms in the central. Okay. So central side, if you increase the physical length, then what happens? This here is much more. And if you reduce it, then it will be lossless. So laser intensity increasing will increase the depth of the frustrated side. So frustrated side there actually plays a very major role getting higher negative temperature because you are getting greater local efficiency in this case. And in this case, this is the omega is the frequency of the explosive unlimited. To expect no kind of intuitively understand increasing the explosive term, you take the metals away. Linked to our layer localization, the same thing is reflected here. So a normal classical understanding works in the increase localization. So let's now consider centers. This is the with the periods. If you increase the period, okay, and then also yeah, this increases numbers. And this is the exact, measurements with these two parameters. These two are the most important. These are lattice parameter, segment parameter, and you see that exact values of it. And then we have fitted it. We have rounded up. You don't have to calculate because the formula is given. You can just pick any one and then you can. So basically, next thing is that tenders is localized, which is a yeah, very importantly localized, I would say, which was first, observed in electron system, but now in there's an experiment in DC now where they show that this is always existing. And this is the way it goes. This is the economic situation. And like this, you can see there's no poles. Some situation you can do it in optical iris. That is what was done in experiment also. And this is the way it happens. This is the intensity is increased. And then how this localization happens. We have a single spike, and that's the localization which is different from a normal localization it comes. So you can see from here, this is the area. So this is beta. This is the participation ratio that how many number of atoms the towards a few sites, etc. Right. So this actually, this is a localization. Normal localization. A cloud will get, if you make the monitor intense and intense, then you can extend the cloud all the way to the center. Localization, you're getting a right? Condition is given by this from the above, but you can see that it goes down to some values of there, which is the place that goes to the center of the region. That's quite different direction. And then we see that the total of the power, as you can see, this is the density, which was exponentially there. When we have theoretically proven it, that this is coming exponentially there. Also, the variation mechanism. So, our understanding of polarized cloud can be easy here. This is detailed in this book. And we have also move the cloud with a change. And then you see that there are four rivers, collapse and rivers in this case. There are normal localization, then others normal localization and so on. So we have to choose area and then these are all very specific. So you can actually choose. And yeah, also the so this is reported recently. So this is the last word which which you want to mention. This is about where we have already moved, right? So then this is the mathematical lattice. We are getting to this video first because the lines are new. Map also especially applications of this. So here this is very new fair. Over critically. We know that when formation was a superposition of this was the most acceptable superposition of it and down. So here this is the potential which we use, and this is the row where which you can look at the first one to understand it better. This is the optical lattice, but very shallow. You can in potentials, right? So simply done. But if you execute, suppose you get this fluid where you have the meeting mark, the background, and then you have another mainstream. So this is what makes it solitary explanation. So this we have actually example shown that the formation mechanism of and actually recently this was experimentally also. So we will experimentally also in DC. So now applications start be looking about quantum information side in the resistors. So this is with dipolar DC, we're not getting into mathematics, just the equation I'm saying here. And then the trader are actually modeling. So what I'm engineering is not dipolar interaction, I'm changing it. So when you trap, so you modulate in that case. So then you get equation of motion for position and the middle. What you get is you can actually have a technique for with all experimental parameters you have done. Tuning for like this, the frequency as well as to the harmonic graph. To the harmonic. So in this is the first one, when we modulate the harmonic is a modulator. You see the frequencies, low frequencies. If today this Q is for 0.5, and so you can see this one. So this is the position of central mass position. So we and you can see because the things we identify those frequencies. And this gets to where we modulate the frequencies. Get both of them on it. These are very good. But frequencies are not very easy because you have some arbitrary frequencies, what combinations of frequencies here. Even value of this need and this is nature. These are all ID. So this is the kind of control of the positions control, right? Presence of the system. And so this is the published in because we got transaction of us. So this is the longest running service channel. Since people have need to use this channel. And this has come also to the so this is our just okay. So now coming to the precision measurements. Now precision measurements in quantum system, what happens that how precisely you can measure parameters. So you have to go to quantum domain because in precision domain you can make the apparatus sophisticated and sophisticated. You can also change the method. Then there are some limitations of noise and errors and other things. But in quantum also those things are there. But the fundamental physics, if I do consider about noise and those things, the fundamental physics allows more precision in quantum system. So quantum precision results are very important, without which you cannot find. So the first one is strong and weak measurements. Strong measurement, the packet mean of positions. There are two packets measurements. Then there are interferences. So this is strong measurements. I can have also imaging that depends on the system. But the weak measurements when the clouds mix as well. Okay. Then also you can have so you can actually couple to another bar. Then there's an amplifier. This separation. There is no separation, very heavily your separation. You cannot measure the cloud separately, they are distinguishable, but you can have we have actually done with the system. We see all the things depending on some experimental model here. In harmonic trap, it oscillates. Using the same model, it has no it's not still. And you can see the meter shift. This is the amplified amount of momentum measurements for weak measurements. So we have amplified the big value like this. We have this is momentum in this case. And then you can see the mega shift, and that mega shift is calculated to measure the particular. It's a very specific way of measuring parameters in water systems. Uh, rather than monopoles. So this way in 2008. But now this is the direct approach for water sensing, where we have used the system that harmonic trend, and then there is the barrier in between. So what happens that cloud with can actually limit, and then it limits just like a split it. So it's the atomic bill split, I would say. So if you do this, there will be superposition. So we use this model, and there are a lot of experiments. This is our model. This is us. So this is the model T and X. So it's reflected, transmitted, and then you see that on all things happening. So this animation for better bias. One part application, that's what institution. And then the outside, as you can see, now we look at the this thing in three space. So this is a typical analog of it, whatever it is. Typical well connected, and then with filters, you can use light. Yes, is that counts. So it's very interesting to see that actually gives filter also for it. So if you look at the three space, then you see those states at some time of 11.2 days. I will show this structure which is indifferent structure. Okay. And this can be used as I said to non-local superposition to create the reference, which is the main instance of strong limits. And this is the paper Nature 2001, where Mr. Zubair has mentioned that these unit structures, although they are very, very small compared to the Planck's constant, which is an uncertainty limit, but the distribution of the structures are much smaller, but they are not irrelevant. They are relevant. They can be experimentally realized, and they will be the limit of. So this is the scaling law which he has predicted for integral system and quantum chaotic system. And this is the scaling law which he proved for first time for DC. And Yeah. So this is how you calculate. You can see the potential how automation. So for example, this there are two lines, one is solid and one is dotted. Just but both are actually overlapping, but if you zoom it up, you see there are fine difference, which you cannot recognize by looking at it, but normal observations. This measurement, this change, small change can be identified by the structure which I am showing. So this is the quantum precision level. So now, uh, this we can actually have indirect measurement of temperature. Because temperature measurement is always crucial in the picometer limit, which is the highest precision limit. So far. And this was reported in. Yeah, this is the last one. 2 minutes, right? 1 minute. 1 minute. I did 1 hour. So, so this is a new phenomenon which is superly, studied in atomic molecular systems, optical fibers, and so on. Then here at EC, we use a ring version. Okay, this is BC, and now you see that and so then it shows fractional levels. The origin is completely different from atomic molecule. In atomic molecule, it arises because of linear energy spectrum. Here it doesn't. It is just a normal evolution, superpositions, and they fail. So we analytically prove. So this is the initial count. Remember, you can see that how many parts it will be moving with trap, like experimental parameters, how a trap should be designed to have a prominent cloud which can be measured in depth of field. And then this is the trap, this is the cloud. And then what I like this, then things will be over. And you see that this is a very fast animation. You can start 4, 2, 6, 8, and so on. You can separately see those experiments of such things, but they have not never noticed this should happen. There are different kinds of shots of these different groups. And so this phenomenon is already very useful in other systems. So we are actually predicting that this will be, when this is in terms of perfect and perfect function, these numbers are all how many states they will be having. So if they are mini sets, looking similar, smaller in shape, because you have to count the number of atoms. So yeah, so this is a we have important thing with PRA 2020, and this is a where switch off the trap, it's still staying that way to have a quantum sensing, but real superposition in spatial superposition, superposing each other, just like it's in. So on that, so the epilogue is that I am more or less trying to disturb different localized excitations, application of 22 information and precision levels. The work is never complete without finishing the members. These works are by Boron, those the students, those are Vicky, they are around. So, I thank to all of you also for. Uh, so, which actually gives the shape pattern. So basically, I divide the main lattice side, depth of the side, and the prosthetic side. It gives me the actually idea that how much it will be trapped. If that is it, why is it that like and then different kind of places are given for different data indexes. It's a physical data. Zero. Zero means zero means whatever. Okay, okay. That's depends no, but and this coloration is more in active interaction. No, we have seen because if you should use the active interaction, link these to them. So basically, because of the track, they will come close. And as soon as they come closer, In the neighboring sites, they look at because the depth is increasing, just immediately look at the dimension of the depth and then you get it. No, that is my interpretation, but like that, we use nowadays. I don't know what was it say. So mostly will be on in the last example it was 80. No, thank you. Yeah, that's yeah. Ryan, no, it's not this. Yeah, this week. Good morning, all. Thank you for giving the opportunity to talk about our work. So to present this, my job becomes very easy if the first speaker is a Professor Conrad who introduced everything so beautifully. So I can jump many places. And also I'm very delighted because Mobile is we are joining the session whose sports we are using uh, each and every day. So discussion. So quit and sorry. So from going first, this place from our Bennett University, it's in the outskirts of Delhi, in the Delhi NCR region, in the Greater Noida, to be very precise. And if any of you are planning to go that side, please let me know. What is the host? But then, on the top, first we'll introduce quantum liquid, and we are separating at this moment the quantum liquid into magnetic DC systems. Then I will go to our recent works. Okay, so this quantum liquid, it was first actually proposed. There are propositions already, but one of the you can say impetus given in 2015 in the petrol creates quantum liquid state starting from mixture of quantum gases. So you will see in the binary DC, so component designs can condense to create quantum droplets, which is now popularly known. So these are nothing but some small clusters of and which is balanced by attractive and repulsive forces. So balance becomes an important part. And in that context, when we propose that the first direction in the matrix general in the discussing the gross Podolsky equation, nobody usually takes into care because it's a very minor Okay. So in the Ross-Petrovsky equation, actually this part is taken into account. So it better argue that this part is the role if the mean field interactions, there are several effective mean field interaction is close to zero. So this part then plays important role. So the new which was actually proposed in 1957 by Lee Wang and Yang. In 2018 came in binary BC the observation of quantum liquid, quantum droplets. It was in position 39. And after that, from the same group came the observation of transition from bright solid to quantum dot. So this into this talk, I discuss both the aspect and the droplet aspect, and we are trying to connect from solitary to droplet or from droplet to solitary. So these are the main objectives for me to discuss. Okay, so for if we to the binary BC, this is a very standard binary BC expression. Here, this is intra-species interaction, and this is my interspecies interaction. So what happens actually? This is pretty well known two regions, immiscible region and miscible region. These regions form these two components or two hyperfine states of 67 revolution 39. Two hyperfine states are used there. There is a kind of segregation of the two components. So this is my immiscible region. This is my miscible region. For these regions to reach up to these regions, the interaction, the competition between interspecies, intraspecies interactions has to be need to follow these definitions. Now, these interactions have to do these interactions by resonance very precisely. So there can be situation like this for the attractive interspecies interaction. For the repulsive ones, unleashed condensate and physical collapses. In this region where it is closed, closed means I define a quantity like delta G, where this G12 plus this, and delta G, if I consider goes to zero, so that means the effective mean field interaction is very big. There, the pure mean field term, which was introduced in 1956 by Li Wang and Li, explain in general. And the class atoms, US terms. So, consider for our purpose, or actually consider elongated. Uh, and in general, for this two component BSC, what they later after the science paper, in their PRL paper, what they propose that if you take there is an identical spatial modes, you can actually reduce the component BC equation to an effective one component equation. In this part, if you see this party nonlinear. So here, this is my usual cubic nonlinearity, which is there in the equation. Everybody is very much familiar about it. Since something new, it arises due to this beyond mean field interaction. Okay. So this was our starting point. This was on quantum instance. This is for experience that if quartic nonlinear Schrodinger equation is really being tackled. Maybe some may say that it's never. We try to find in depth, means me, my students, we try to find, but rarely found any literature where these two interactions are big distance. Talking about things go to other fields, nowhere we see this one odd and even exponents of nonlinearity has been taken care of. These were the many things. If we don't know how to tackle it. So what did? So let's come look at it later. So this was the starting point. And one day for analytical into the analytical, making it analytically more easy, we wanted to study this problem quasi one dimension. To reduce it, we have with the unknown prescriptions. We consider a strong confining universe confinement and allow the condensate to explode in the longitudinal direction. For that, if we use this type of an uncertain solution, we can actually see one dimension Ross-Pedowski equation with coordinate nonlinear. So at the time being, we consider the external harmonic trap going to zero. We'll come into that later on. We'll discuss. Well, as I was telling you, we did know this problem even analytically. We are struggling. So what we thought that for regular GP equation, it is actually it can be mapped as a Jacobi electric equation. It is some CN solutions, SN solution, quantum solutions. So let's try solutions for this. Okay, so before going into the fundamental solutions, actually, there is one more thing I'd like to discuss. Yeah, so this is the equation we'll handle. Now it comes the issue. What happened in 2016, Jan Petro's another paper, what actually is starting from the second country. So in function. Now, here, before getting into actually our problem, we must appreciate the difference. This is Petrov's equation of motion in 1D. This is our equation of motion in quasi 1. And what we want to do is more experimentally available. In 1D, we can have BC. We can liquid or something, that's what we're saying. But we can have BC. What we can have BC? We can have BC in quasi 1 dimension geometry. Okay, so here you see I have a cubic nonlinearity, usual with repulsive interaction, and I have quadratic nonlinearity with active interaction. Now, if I come to a quasi one-dimensional system, I have cubic nonlinearity with attractive interaction, and the beyond mutual contribution here is what considered. So this is the fundamental difference between a 1D system and a quasi 1D system. So if I did as I was telling you, and I was we were not sure of that, we just took it as fast as a mathematical problem. Just consider a differential equation which has this type of nonlinearities. And we can have some solution. So we see that if we can do some track management, we can actually obtain some set of consistency condition, and from there we can obtain certain solution. Here straight lines of the trap potential, and here these blue dots are the solutions. These are very much constrained, and we have to do some track engineering. So these solutions we also realize that since is that we know that if you take m equal to 1, it will go to the high. If you take m equal to 0, it will take trigonometric case. So what physically it means, it will go to a balanced solution for m equal to 1, and it will go to the sinusoidal means m equal to 0. So what we thought that if you look into it, see if you put m equal to 0, you can see it's nothing but so m equal to 0 under this structure is what we have made. It's not working properly. That was another conclusion we were able to draw from this section. You can always go to SN and DN and so on. But now let's come to physical. Again, I repeat, this was the equation. And again, I consider my A is going to means A going to 0. And we change this answer solution. We obtain this set of consistency condition, and when we replace these consistency conditions in the equation, we landed up that there is we can only have an analytical solution if the mean-field interaction and this mean-field interaction is related as these relations. So get two solutions, and then we do the stability analysis. We find that this part this solution shows stably step, and we find this is more stable solution. And of course, we do it numerically. We didn't numerically different or analytical solution. Let's come to the context of the problem. So here you see that these are the signature of the quantum problem. So constant density. Well, so what actually happens is I have competing interactions. I have attractive, effective mean-field interaction, repulsive non-meaningful interaction, and because of this competition, I can do a monotonic kinetic function of power. So it starts actually from solitron formation, and then at equilibrium density, I can have here, this is this point. Equilibrium density, we can have the droplet formation. Then again, droplet starts to break into solitrons, we add critical density. Right? Process, the energy functional becomes negative. So here, energy function is negative. We can split these just theoretical expressions and we of G and G prime, we get an equilibrium density of 6.25 and the critical density of 14.06. But when we we calculate the effective effective energy, we see that the equilibrium density is not that exactly matching with this 6.25, but critical density is matching very well with this analytically obtained expression. Okay, so now as I have said initially, I have taken K equal to 0 for my analytical years. Now let us take into account K not equal to 0. So we do, and what we see, if we play around with the strength of the longitudinal function, we can actually from solitron state. So this is just giving the external potential numerically we bring it, we obtain, we can see this kind of localized structure, this kind of a bell structure, and again a structure kind of structure. Okay, so when we have it, then we must calculate the energy and chemical potential. We see the energy and we see indeed at the flat top region, their energy is negative, chemical potential is negative. Is this droplet to solitron transition? Is it a crystallization? Is it a proper? That's our next question. And this is the region actually I try to the gray region. I try to mention it as some kind of a crossover region. So what though there is non-monotonicity in energy and chemical potential, don't see any abrupt change in that. So we consider it as some kind of a crossover. This assumption becomes more validated when we calculate the droplet size, which normalized by the largest size. We can see that the most transition from droplet to the solitary state, where of course droplet gets flooded, so the size is expected to drop. This is the input. When we calculate the peak densities, and we see that for a certain region, the peak density remains constant. And which is the signature of the peak flat top peak density. And then after a certain time, magnetic density starts increasing. Here we try to plot N versus P. So changing the particle number, we are at the trapping string. What we see is that this is the region, the droplet region. So when we do a particle number, means if we were talking about exact number, say already theoretically it is shown experimentally. So say the particle number is the order of 2, 4, something. We actually observe from the solitary structure. 20, 30, we usually see droplets. If we see here, the plot we have said, this is it will go to the solitary state. And this part is solitary plate to solitary kind. And they are not to manual. So then we thought, let's study the basics. Starts the dynamics with what's that like so, so we start it's we start with the solitonics. And thing is that whenever we talk about this, I'm talking about the mathematics and all these things, but what precisely we can apply it as applications. One really important application from the context of space wizard and another is the inertial navigation system. So for inertial navigation system, what actually that comes into play? It comes to play first of interference. But interferometers are nothing but the natural counterpart of the standard detector. So you power packet using some optical techniques like vector pulse, bivalves, and this, and then you recombine and also interference pattern. Actually, you can do very precise change. So from there you can make a gravitometer, and when you have a gravitometer, you can it in what range of carrier events for underwater levels, so the water levels, oil explorations, navigations, inertial navigations. So, so, so in context, here we have some impurity, and in the schematics, the impurity is shown as a kind of potential. And I consider the solitary system, there is a trap is there, but for the initial case, again, we will switch off the harmonic confinement, we will do without harmonic confinement, and at the end, we will do something with that. So with the solitary is coming with some velocity, and we were interested to see it reacts to this impurity. And this is my governing equation. So here, for analytic calculation, we consider the dimension like potential, but for numerics, we consider potential one or even potential area. We actually consider both here for the generality and just show you. Was the variational method when we divide the conserved function in a solitonic component and another one is a trap mode. System Lagrangian and solve the Euler Lagrange equation, then we get a large set of coupled equations. Large set of eight, and there are actually 8 coupled equations, which you submit some process you actually see for different potential strength. You can see transmission,
soliton, you can see partial trapping, you can see full trapping, and you can see reflection. So phenomena can be observed by tuning potential. We verify is when our effective data. So if we compare it, as I have said, we did it for potential barrier as well as potential method. So potential barrier actually was not that interesting because there we were able to see only transmission and reflection. But when there are many situations came up, transmission was there, partial tracking was there, quick tracking was there, again complete reflection was also there. But what we see there is numbers same order of magnitude. Of course, they are not exact, and they are one must understand that relational method is calculated with the delta potential, whereas effect is calculated with finite potential. Well, so then we employ the trap, and if the trap is weak, in effective we see some splitting and recombination can be observed for weak trapping, but if the trapping is strong, you got population of soliton in a trap, which is why we been reported already with 1/2 times of longitudinal soliton oscillation frequency. Yeah. So these are actually, if we need to work further, we need to go to the drawback side to study these things, and these things can have previous implication in the context of interferometric studies. So let's draw the conclusion. So what we did actually, we discussed the recently observed this exotic liquid phase, derived the possible cubic quartic analysis, describe the possible conodal solutions and analytical solutions for CQ analysis. We have provided. Then we try to draw a droplet solution droplet phase diagram in one-dimensional geometry. And then we investigated the solution techniques when it's subjected to an impurity. So with this, I like to thank my collaborators, Dr. Orva Devna, Professor Onabazu, and Professor Tushar Panigari, and also the funding agency, DSTSCRB. Thank you very much. Good things. Yeah. The last because okay. Yeah. This is the your yes, this gray is actually what we have kept the weather. So so now so yeah, like I one of slide is shown the condition for case relation in primary views. In this one
We have some G actually.
we got square root of
Yeah, G100.
is it for the loss probability or because since you are having potential. Calculating for the transfer. So here, which were actually next for? Here mentions rates.
It's still 1,000. It's there. It's
This is a powerful in general. But when you have a potential, you no longer have this condition, right? When you have an estimate that the expression not following this condition. Different from the external potential of linear coupling. If you have binary, okay, so this binary, the two components of AC, there are interaction between the same species, and there is interaction uh, between the two species. So this is actually, I am not taking considering the trap at this moment. Just in general, if we have a two component BC, then interaction will play out. If you put a trap, there can be a connection with that, another tuning parameter that can come up. But here it is, we're not considering it.
Yeah. That's one thing that in the last application, you mentioned data function, right?
Yeah.
So for V naught, right? Yeah. So when V naught is one, you have taken.
Yeah.
What happens actually when the cloud propagates?
Yeah.
And depending on the width,
Yeah.
if it is very narrow, then there will be no flapping. But last table says that if there are flapping and reeling,
Yeah.
then it is not a delta function.
Yeah.
So it should be like very narrow.
Yeah, exactly.
Because unless we know the other scale, we do not know whether one is very small or not.
Yeah.
In this case, I think tracking is not meaningful because delta function is there.
Tracking, yeah. You want to make this tracking or this one?
No, the delta function.
You can. The point is, this delta function is used for additional calculation.
Right.
And for effective, we haven't used the delta function. Effective, we use this tracking, this potential web. Then we are.
So that is the point when you compare.
Yeah.
This feeling cannot have a clubbing part because it will all scatter.
Yeah.
Go to the next table. The table, actually. Yeah.
Yeah.
So here, yeah, that trapping, function trapping. I think this happens when the trap is reasonably wider.
Yeah.
Cloud will fall in.
Exactly. Yeah.
And then they will trap. So you get like a mini
Yeah.
delta function potential, whether it may be a minimum potential also.
Yeah.
Scattering.
No, no. In the variational calculation, it actually showed. It is the variational calculation with delta function.
Variation is
Yeah.
the other.
Yeah.
Yeah. Okay. Okay.
These are like 100. They are plus one analysis. In other words, they should be like a spatial vector. So are they dissipating nature because there is the dissipation. The dissipation is there, and there comes the role of three-body interaction. So there is what which actually about droplet dissipation due to the three-body interaction. Only in modern dissipation without here at this moment, I'm still taking into account any dissipation in the current calculation, but of course you can take into account dissipation. Using the recent studies where they talk about the keyboard interaction. So that's actually equating nonlinearity with the real part and the imaginary part. There, the imaginary part is giving in the dissipation. So there are some. One initial point, again, this 2 DC component was like 1 DC. Yep. Now, if that region, you have made that application as it is being mentioned here. Yeah. So it is in that, of course, in that OBC, anyone cannot do that. Anybody cannot do that. This is the region of influence where it is actually collapsing. And this delta G is going to zero in this region. It is filled up. If you make this kind of a section and you boil it, then it will boil it down to some kind of an effective one component.
So this thank you. Yes. Take on. Showing one next and reference. Yes, I like it.
Morning to all. And thank organizers giving me the chance to present our work. the work which I am going to present here, we have done this. She is my PhD student, and she has completed PhD. And basically, we are working on the things which just for some fun in discussing that we are trying to study the dynamics of this protein nucleus. It would be point out that if we consider like BEC, then we can achieve a quantum liquid state. Like if we are just considering a single component BEC, in terms of productive relativity, uh, we are not getting any external term. Then, we- but you pointed out that if you take a two component BEC, in which you have uh, um, it's a so it considers one sufficient too. And if we are in a reason where these are two same components, then these for this mainstream and non-mainstream will be something in the repulsive region and the system will behave as a convergence. If it is a mixture fluid state, then case this meaningful interaction feature. The speech of this meaningful interaction will be will will become comparable to the non-meaningful interaction, and basically it will lead to the creation of this protein state, which is known as the human liquid state. Also, the proposal by Petru is considering this formation of profit in the influence of this non-meaningful interaction and meaningful interaction. Where Volvo has also proposed similar kind of profit structure in a two body and three body interactions. The single experiments was not able to attain that particular comparable state of meaningful and non-meaningful. Experimentally, the rate was observed in two body interactions. So in super system, in two component DC, two droplets exclusively realized the mixture condensate and the hyper. So this solution, right, that if we consider this rate in the 200 case, then we increase the particle these are increasing that it is signature of droplet profile. It is indication feature of partner. We also post uh, things say in like this chemical interaction is very with the time after this second meeting. Then we can have a relation preference in the pre-place domain. Uh, Next, now look as the profit profile in the one system for this radiation of particle. They have calculated the collective excitations of the system and shown that as we gradually change the particle numbers to the exact calculation and variational calculation, we will get a profit profile. These three which are reported recently are in the free space region. So, the we study this particular system under influence of variety of external confinement and generate a analytical models. It's analytical models like Mr. Khan was just discussing that it's very trivial to obtain the exact analytical solution the moment when we any kind of external tap on the system. So motivation was that Actually, we have 90% variety of numerical models for various kind of external situations. We never want to completely see a scenario. You know, if we I'm going to have actually how to present in the conference. But the recently our group has included the droplet experiments that started coming from it. They changed the uh, instruction. Instruction. Maybe anything will uh, explain the one of fluctuation curve. And with that particular change, they have shown that they can switch from the top file to the front. So it's good to see that it's possible that and some external you can have this kind of transition and we use some kind of trap something, then rockets can be used to be talking those kind of systems. So looking at our idea is that we want to what takes in the names of track and we are interested that can be the analysis of the system in presence of rich bed of optical lattice in various experimentally relevant scenarios. We are interested to construct a generic unified theoretical model, which is from we can generate function shapes or droplet in presence of various kind of solution. We have to be the generic idea, which is widely used in the Solcom literature. Like we start with the analytic solution. We take it as some solution and solvable differential equation. That we obtain consistency condition about the future parameters of the system. If we are able to solve these groups of equations, then we will obtain a wave function solution for it. So we when we see and obtain the one dimension this standard GE equation, the thing which we have taken here differently is that the strength of the interaction are here is PSM. So become complementary. So similar case, we are taking it of that. We have a harmonic oscillator, here time dependent oscillator frequency. So if taking that the one of structure nonlinearity is time dependent and the cubic nonlinearity is also dependent. If I compare it with the results which are obtained by the movement, uh, we obtain this particular wave function solution for the three phase situation. They have not taken any external confinement. Using external intuition, we have some from here. The signature of the signature of the data profile will definitely come into the wave function. So we wave function and the consistency conditions and take a cut in the oscillator frequency to the wave function. If I compare this wave function, which is obtained by the Malamet group also for the free space scenario, the different for case is that we present with this particular underroot density factor. Here, this mu is basically 2 by 9, e by 3, so they are same terms. So the presence of this particular term, this can be used from here also that this anti, which is the oscillator frequency, is connected with this particular dramatic filter. So the T is constant then this term will become equal to 0 and we will reach to a free space situation which is earlier reported in the literature. So, complete our results with the reported results for the free space situation. So for that case, we have taken gamma t equal to constant so that we have no confinement. And we change the strength of the chemical nonlinearity. Now we have the you know the graph switching from file to separate file. So the impact of external confinements into the two different forms of learning. But also we have obtained the whereas we are obtaining the exposure harmonic track. And this one is from a free space situation. And when we put a harmonic trap, regular harmonic trap, then we are getting this particular combination of this reflective in the regular harmonic trap. With a exposure, we have a self regular quantum droplet profile. So this is a physical understanding of this regular applications of these regular and explosive overly nonlinear. We have reported this particular result in this journal. Next, we started to focus on this particular harmonic case and start to study its temporal evolution with respect to this student nonlinearity and the idea is that we are trying to see that the kind of property silicon transition which has been shown by the Torrey group, we are able to obtain similar kind of transition from our mathematical model or so when we study the dynamics of the property, we have observed that there is a strong combination at these uh, locations. And so analyze it happening so being this nonlinearity which is coming from our analytical model. And this is for the generation of this regular harmonic trap, we are taking gamma t system t. So basically we have then you have the same profile and oops, that highlighting. We have when you are researching pretty rest of this particular topics. It's happening that it is a situation where the mean field interaction is completely balanced by the beyond mean field interaction. Here, in this region, the parameter 3 by 2, we don't have any presence of beyond mean field interaction. And we have only human interaction. So basically, from parameter 3 by 2 region, we are in the solid regions. Whereas from 0 to 5 by 2, we are in the existence of that both the competing nonlinearity must be present. So on that basis, we have constructed a field which indicates the transition from solid rocket and reverse. Uh, Given the current solution of this investigation, we have connected to the frequency function in terms of CN function. And this helps the What's the different aspect of this droplet? We observe, like if we keep uh, uh, oscillator frequency in the range of 0.75 numerical values, and we choose some values which is less than 1, we have observed is that we have single droplet which is fragmenting into three droplets, and it is fragmenting more droplets, and then it is not in it. So basically, it is a fragmentation and recombination of droplet, which is the understanding related with uh, uh, the uh, nature of the solutions which we have taken here. We have taken this particular behavior for different M values. And we observe that cleaning of this particular M value is basically controlling switch out. So the lesson which we have taken in this particular harmonic is that it means those a difference of um, a which is practically like sometimes which we have taken of that game. Is instead of bounce in this particular droplet will be oscillating in term. Any let me start calculations get with the choice of this oscillator frequency. Next we'll move towards the explosive harmonic trend, which are similar behavior in the explosive case also. So that we have taken self-harmonic form, which gives me the explosive phenomenon. This is the wave function solution for this particular case. In comparison to the previous case, what we are getting it up here, that if we are choosing the gamma as a positive number only, in that case, we have to only choose positive number to obtain the droplet file. We in the droplet phase if we are working with the explosive trap from our constituent moment. We check out of on this something criteria that is so we proposed wave function solutions on this in the sense of components. And we observe interesting properties silicon transitions in the thermal system, actually the oscillator frequency of the trap. And we also observe fragmentation and properties. What I get from that find our work for various other kinds of confinements. And one of the confinement is the theoretic confinement. So we work very important for the quantum droplets in presence of optical lattice. And there is a rich literature for the confinement, and it is a really rich test bed to understand the variety of quantum which we have taken is basically motivated from this particular in which four optical lattice were reported and solitary wave solutions were obtained for the 1 dBs. So this is a experiment. If you observe, uh, this is a, this is a full color lattice, and has a exponential function. So this is uh, of sorry, that's the can have body so these things can perform the cells which we can generate. So with this choice of potential, we want particular Ideas with this particular one-dimensional dimensionless basically equation, and with the uh, beyond mean field space dependent here, beyond mean field dependent linearity, and this cubic nonlinearity is again space dependent. Basically, this choice is motivated from the choice of the external terms which we have. So we have taken the generic form of the wave function solutions. This is we have taken the dimensionality of optical analysis from this generic potential. Based on the choice of this particular P1 and P2 parameters, we can switch from single optical lattice to mathematical optical lattice, optical lattice, or focal optical lattice. And if we take this particular last term, which is this subset, then we can have multiple optical lattice. So you can observe that this potential is very rich potential, and it is giving us very large kinds of plan for the system. So we started from this case where if you observe here, we have two important pictures, one P1 and P2. So P2, then we have focal optical lattice. And if we take P2 not zero, then we have focal optical lattice. So we first take three situation where the results are already reported, established. We take this scenario and obtain a blueprint. Let's begin choose P1. Here P1 is basically this first process case which is in control, and this two case. This is a VOL. That is the sign of P1 is negative, so it is designed like a pure figure. So we have its whole system is figure analysis. So takes the straight hospital P1. Yeah. The brain what is operators like. But we are not observing any kind of uh, uh, signature of this localization or any other thing in this case. Let's look at this P1 positive quantity. The choice is that, well, if we take this P1 positive, so then we have this particular complete linear limits, basically it's not a case. Case. If you are observing this change in the strength of potential of VO, then we are directly obtaining a disordered lattice or dichromatic optical lattice. And the signature feature of localization is observed on the density lattices. Primarily, this density lattices are localizing, and they are localizing towards the center of the system. And it is concerning the kind of behavior which we have reported earlier, in which we have observed localization, and that's my localization in the electromagnetic limits. We are observing one more another aspect of this localization in system. And to another thing, we focus upon obtained form of nonlinearity. If you see that horizontal axis is basically the magnitude of the potential depth which we have taken negative and positive both for moving from optical lattice to pragmatic lattice. If you see that, negative is that field and mean field nonlinearities are complex, and that's why we are seeing a field profile in the system. The droplet profile is not appropriate. If we take source of P1, then this interaction is dominating over the beyond mean field interaction, and the balance in between them are disturbed which is leading to moving towards the solid region. Yeah.
Since it's the user base for questions.
Oh, yeah. I will make it complete. So, uh, observe these kinds of results for the negative template for the four optical lattice mouse. So, and we get from the results for the system uh, using the SFT analysis. So, we have observed experimental solutions for the molecular optical lattice. I'm just presenting one more result in the control. So, we try to analyze this system for the negative temperature scenario by taking a explosive trap and the optical lattice, mathematical optical lattice trap. We have basically shown that uh, is sufficient enough to obtain the negative temperature in comparison to the combination of explosive and lattice trap. We choose the combination of this first we choose this pure automatic optical lattice, and we calculated the wave function solutions, and we obtained the one this situation and change the potential depth of this every we are observing the localization. We investigated the temperature of this particular system, and the problem is point is coming into the positive reason. Only when we shift towards the explicit trend, sorry, when we shift towards the with the change in the horizon base, here, here we are getting a disorder in the bridge here, and we are getting a moving to our temperature. Well, it's like we have reported in the scientific reports, and we have confirmed for this particular system properties we want systems also. So, uh, if I summarize, we have obtained an analytical model for the negative temperature also. So basically, we have calculated the exact wave function solutions for the memory trap, multi-layer optical lattice, and negative temperature situation.
Thank you.
This is
Communication from the sequence of the diagram to the confusing with the explanation.
yeah. So I like what my results. So there are instances that here they are commensurate. So if you focus for these things, the form of patients which we have taken here, you see that here this is 2kx and kx. So we have a limitations that should be a commensurate. But experimentally, it is also possible that you can have incommensurate mathematical lattice. It's possible.
Speaking of related people with administration ones, when like on increasing fever, the droplet profile is like being like somewhat shifted to a solid or like
Yes.
and which the reasons behind it.
Yeah, so that's what I we try to analyze. And for the obtained case, we have analyzed the form of mean field and beyond mean field interactions. And if you see here that if when P1 is negative, the magnitude of mean field and beyond mean field interactions are completely comparable. It is essential requirement for the existence of problem. But in the positive magnitude of P1, when P1 magnitude is very large, you see that this cubic interaction is dominating, very strong in comparison to the beyond mean field interaction, and which is disturbing the droplet state in your in the solitonic region. Oh, yeah. So P1 is basically connected with the strength of potential. you showed that in droplets, even without an exposed to traffic, for example, I think it's a can consider part of the. Yeah, we have already we have reported that particular in this particular thing that this we have shown and we will no, no, yes, yes. This
Even strength, interactions. Why you think that changing the strength of harmonic trap to change it to droplet to cycle and then physically why?
so basically it's happening when we are changing the oscillator strength. We are changing the strength of non-linearity also because F is connected with
Yeah, true. For droplet, particular combinations.
yeah,
And you are well within that range.
yes.
And then you are changing that goes from droplet to cycle. It's very surprising, right? Basically, I don't relate this things. Definitely, it must be happening. Basically,
Actually, it took motivation from China, itself, in which they changed the basically to the certain length to change the non-negative strength. So when they are changing their their scattering length with time, so they are changing their non-negative.
yeah, that's happening.
Yeah.
So have that computational. Very,
Okay. Thank you, Sajid. Correct. Thank you.
This right there. Straight teeth. Yeah. Yeah. Yeah.
Morena, जी तुमने एम कर लिया मम्मी पापा ini sudah takut kan ini afternoon baru tak laptop
Oh, in that case, there is either basement. But what's that?
Well, it's a file here. LOC, LOCA, take PDF. See? I think it's a PDF file. No, not process. It's process. Zero. Who's starting? Who's the chat? Oh. This was what was some paper. Chair. Some Surely there is in the council. Really? Yes.
We don't communicate on the login. Wait, no. Yes, okay, yes, yes. This, yeah.
Okay. Well, good afternoon, friends. I'd like to start off by thanking Dr. Nityanand for the kind invitation to be here. He and his colleagues have organized things so well, and it's really very comfortable. Thank you for putting in all that effort. Second thing is, it's done on a very special occasion, which is the 60th birthday of Professor Poncheshan, who was a friend of many of us. So I'd like to dedicate this talk to him, as a matter of fact. Yeah, he's had a lot of interest in experimental issues, and as you'll see, there's an experimental context to this talk also. So the title of my talk is Cooperative Kinetics of Living Liquid Crystals. And by cooperative kinetics, I mean synchronization in the sense of nonlinear dynamics. Various terms will become clear as I go on, so don't worry. None of these terms will be left sort of unclear. And if particularly the students, you have any doubts, please feel free to ask questions right there and then. Okay, don't wait till the end of the talk. So let's move on. Here's an overview of my talk. I'll start off with an introduction to the system. I'll tell you what living liquid crystals are, and then talk about the modeling of these living liquid crystals. These living liquid crystals, maybe I should already say at the outset, are composites of active matter and liquid crystals. Liquid crystals have been of interest to the StatMech community for many, many years now, and active matter is a subject of very recent interest. So this is a system that actually combines active matter with the liquid crystals. Okay, let's formulate a model for living liquid crystals. Let's talk about the kinetics of that model. And here I'm bringing sort of various nonlinear dynamics phenomenology. And then I'll end with a customary conclusion out here. So let me start off by introducing the subject of active matter. This is something I think Manish Srimali referred to in his talk also yesterday. But let me just repeat it because it's been a subject of huge interest in statistical physics in the last 20 years or so. Huge interest is that one of the pioneers in the area, Sriram Ramaswamy, is our colleague in IIC Bangalore. And he's really been world leader in this. Okay. So the question here is, as the name suggests, active matter is a collection of self-propelled particles. What do I mean by self-propelled particles? They consume energy and they translate it into motion, basically. And a self-propelled particle can be a bird, it can be a fish, it can be all sorts of bacteria, and so on and so forth. So basically, these are systems consume energy from the surroundings to move. These are intrinsically non-equilibrium systems which violate time reversal symmetry. Okay, so it's just a sort of technical side here. Okay, so you've seen some of these pictures. And they taken from this review article in Reviews of Modern Physics, of which Sriram Ramaswamy is one of the co-authors. So you have a bird, and that's sort of picture we've all seen in the sky. And you have fish shoals, and this picture you see in aquarium. You have bacterial colonies, vibrated rods, and so on and so forth. Okay. Now, for a statistical physicist, the big deal about complex systems, and these are all examples of complex systems, is that the simple nearest neighbor interaction can lead in certain cases to long range order, basically. Okay. Emphasize you're only interacting with your neighbor or your next neighbor or some such thing, but the entire system is to have a ordered state. So, for example, these birds are just trying to avoid their neighboring birds. That's all they input into it, and then you get this swarm of birds or a flock of birds moving in a certain direction. Similarly, with the fish and the bacteria and so on and so forth. Okay, so the system breaks symmetry under certain conditions. and those are the phase transitions. And I address okay. This class of very important systems, actually even older systems than active matter are those of liquid crystals. We encounter liquid crystals every day on our displays, in our TVs, in our phones, and so on and so forth. And again, let's sort of take a simple realization of a liquid crystal. So it's an assembly of rod-shaped particles, so it's like a box of chalks or some such thing. Energetically, the particles like to align parallel to each other. And optically, they like to be disordered, basically. So that's immediately the ingredient of a phase transition out there. At low temperatures, the system wins out, the energy wins out, and you have an ordered crystalline state. So you have both orientational order, things are aligned parallel, and you have positional order in terms of the location of the centers, rely on crystal lattice. At high temperatures, entropy wins out and you're in a disordered state, and you have neither positional order nor orientational order. And in this middle, there's a stating state called a liquid crystal. Positional order has gone, so the centers is no longer sort of sitting on the sides of a lattice, but the ordering on the average, they're ordered point in the same direction. And of course, these liquid crystals have found huge technological application. It's been the subject of interest for 100+ years. And one of the important books on this is due to the James and Prost. This is this book called The Physics of Liquid Crystals from the OUP in 1993. So these two sort of systems well studied, which we are going to consider a hybrid of in within liquid crystals. So that brings me to my system of my talk today. Living liquid crystals, or LLCs, are nematic liquid crystals with active inclusions, with active particles inside them. And typically, these particles point parallel to the liquid crystal. Okay, that's the sort of that's the nub of it. The systems which have just been talked about for the last 7-8 years, and there are huge applications in microfluidic devices, and all sorts of synthetic systems, transport in cells, and so on and so forth. Okay. So I'm just going to show you some pictures from the experiments that got us motivated. So this is some form of bacteria in an nematic liquid crystal. And this is from these papers by Zhu et al. From PNAS and Peng et al. From Science, basically. Okay. And on the left-hand side, you see the liquid crystalline order. So it's very uh, a mix of +half and -half. This is the exact points in the liquid crystals, basically, where the liquid crystals are maximally, that you go around until you pick up an angle of pi, basically. So what one finds in these experiments, that's what I'm showing you on the right-hand side. These are the trajectories of the bacteria. This is the system where you find that the bacteria migrate towards the defect course. Okay, so that's the first. These bacteria like point parallel to the bacteria. The bacteria like to point parallel to the liquid crystal or vice versa. And the bacteria migrate to the defects in the system. So they accumulate out here. So you can immediately imagine that this could be a mode of transporting bacteria away or towards a certain place. Okay. Here's another interesting liquid crystalline configuration they studied. They used boundary conditions to create a vortex at the center. This particular experiment, they found that they were able to channel the active matter to flow in a circular direction, basically. Okay. So you could control active matter and make it flow by just putting the right boundary conditions to the liquid crystals. Okay. So these are sort of various interesting experiments which suggest this is going to be a very important system in the years to come, logically. Here, of course, theorists, so we are interested in modeling the system. That then brings me to class part B of my talk, which is the modeling of liquid crystals. Okay, and again, we're going to follow the same strategy. We start off with models for liquid crystals, active matter separately, and then we sort of marry them in some form, and then some appropriate coupling term. For the students, the following on the maths is not necessary. The maths is all there in the literature. I can give you references and stuff. try to get a feeling of the phenomena involved and how you sort of would like to model such systems. So here's a model for a liquid crystal. This is a standard model. This is called the Landau, the Jens free energy. And you've already seen this Landau expansions in these Bose-Einstein models people were talking. In the Gross-Pitansky equation, for example, you have similar Landau expansions. So you have, like I said, you have this bunch of liquid crystalline molecules. They are characterized by a director. That's what it's called, a director, as a matter of. And the director on the average points in the directions of the molecules that characterizes molecules. So obviously, if all the molecules are lined up, the director has a large magnitude. If, on the other hand, very few molecules are aligned up, the director has a small magnitude. So the magnitude of the director serves as a order parameter for the liquid crystalline system. Okay. Now, as I said, people write down these Ginsburg-Landau energies. You don't need to worry exactly until you're going into the details. Typically, in this case, you use a tensor order parameter, Qij, which perhaps many of you have seen in your courses. There's a magnitude out here, S, which is the order parameter, which is the magnitude of the director. And then Ni and J are the components of the director, and so on and so forth. And in terms of this Q tensor, you write down the free energy. And the free energy is just a Landau expansion with various quadratic qubit terms and so on and so forth. Okay? This is very sort of standard in the literature. And as I said, you've seen already some variant of such an expansion in the context of the Gauss-Fibonacci equation. And then the kinetics that you write down for liquid crystals is the relaxational kinetics. So the order parameter with respect to pi relaxes the minimum of the free energy dissipatively. So that's relaxation, dissipative relaxation. Again, this is sort of a standard terminology. It has been around and is now even the subject of advanced statistical physics courses. Okay. Again, as I said, you don't have to worry too much about the precise form of the equations. Just get the flavor of how we model these systems. Okay. So that's a kinetic equation for the liquid crystal. And if you plug in this free energy, you can write down the form of the corresponding nonlinear dynamical equation. Okay. Simple free energy for active matter. Well, let's be careful out here. Matter is an intrinsically non-equilibrium system. So it's going to, for free energy, there's going to be some relaxational part to minimum of free energy. But there'll be some sort of there'll be some virtually non-equilibrium input also. So the appropriate order parameters in this case are rho, which is the density of the liquid crystal, the density of the active matter, and P, which is the direction of the active matter, the arrow basically. Okay. So in the perfectly ordered state, P is high because all the words are pointing in one particular direction. In the disordered state, P is low because the words are flying sort of randomly used to each other. And again, just taking this from the literature, you have some form of Landau extension. Precise form is not so important. It has its usual quadratic terms and so on and so forth. And the appropriate equations are due to Toner and 2. This is what actually started the subject. So remember, the density is a conserved variable. So you write down some sort of continuity equation for the density. It has an advective part because of the velocity field, and then a relaxational part due to the free energy. And similarly, you have a kinetic equation for the polarization. You have an advective part, then you have a relaxational part to the minimum of free energy. Just sort of that's the sort of bare bones two models which we are going to marry. So we now write down obviously a free energy for liquid crystals, for living liquid crystals. The free energy we propose, and now this is comes to our work. The free energy we propose is this free energy plus this free energy. So that's F of active matter. Sorry? It's a vector. Own current? Correct. Yes, yes, yes. It's as similar to what you see in EM theories. Okay, so the free energy we propose for living liquid crystals is the sum of the active matter free energy plus the liquid crystalline free energy. That's the natural term. You coupling by hand, and the coupling we put in is this term minus some coupling strength C0 n hat dotted with P the whole square. And it should be sort of almost obvious examining this free energy that when n hat is parallel to P, so physically when the liquid crystalline director is parallel to the local velocity of the bursts, then this term is minimized because this dot product is the maximum. Remember, in physics, you always want to minimize the free energy. That's your sort of preferred ground state. So this term is minimized when n hat is parallel to P vector. And I put a square out there. You might wonder why I put a square. Put a square because the system is up-down symmetric. It has no direction. So it should be the same if n goes to minus n, basically, because these liquid crystal molecules had no head and tail. They were just sort of box pieces of chalk, basically. So that's the free energy for liquid crystals. We just replace the free energy out here and the free energy out here with composite expression and come up with a formidable looking bunch of equations. Again, it's there in the literature. I'm writing the equations down in 2 dimensions. You have equations for the liquid crystal field, that's Q11 and Q12. So these are the equations in the absence of coupling, and that's what the coupling throws into you. So the coupling now sort of connects you to the order parameters of the active matter. And similarly, you have the Toner 2 equations for the active matter, and that's this whole bunch of terms out here and this whole bunch of terms out here. This comes out if you do the functional derivatives. And then you have this term C0, right, which couples you to the liquid crystal. Remember the physics that has gone into this? The liquid crystal will like to point parallel to the active matter. That's the physics that's gone into it. And in the absence of C0, if C0 is equal to 0, then you just have the liquid crystal doing its own thing and the active matter doing its own thing. So that's the sort of, that's where we're at right now. What are the own things of the liquid crystal and order parameter? Let me tell you that also. The temperature, the liquid crystals naturally orders. Okay, so below the critical temperature, the liquid crystal goes into this nematic state. Above the temperature, the liquid crystal is in the okay. Similarly, for the active matter, it's driven by density, this phase transition. I think Manish mentioned this yesterday. For densities above the critical density, the birds order. Does that mean the birds all fly in the same direction, approximately? How much they order depends on how high the density is, basically. Okay. So the birds order in the for densities above the density, and the birds fly in random directions, or the bacteria move in random directions below the critical temperature or the critical density. Okay, that's the sort of physics of these equations. And now we're going to ask, what does this coupling do? These are complicated nonlinear equations, but now we know techniques of nonlinear physics, and we're going to sort of apply some of those to understand the kinetics of this full-fledged system. So the first thing one always does as a nonlinear person is to look at the fixed points. The fixed points, you set del by del t equal to 0. So the left-hand side becomes 0. And you set all the gradients equal to 0 because you're looking for a homogeneous system, basically. Okay. So that's the that's part C of my talk, where I'm going to start talking about the coupled kinetics and about the sort of phase diagrams of these models. Are there any questions about the modeling at this point? It's the philosophy of the modeling. Students, you guys are okay? So then let's move ahead. Set by del t equal to 0. The gradients equal to 0. And there are 3 cases of interest I'm going to look at. Remember, the liquid crystal can be ordered or disordered intrinsically. The active matter can be ordered or disordered intrinsically. So the three cases that suggest themselves are: one is liquid crystal is disordered intrinsically, and where the active matter is ordered. So here you can ask the question: does the active matter drag you into or drag the liquid crystal into an ordered state? Case two, liquid crystal is naturally ordered, but naturally means without the coupling, but the active matter is disordered. Okay. So here you ask the question: can the ordered liquid crystal, due to the coupling, drag you into the ordered, drag the active matter into the ordered state? Case three is when both of them are ordered. It's not a very interesting case, basically. Case four is even less interesting, when both of them are disordered. Both the systems are essentially dead, and together also they will be collectively dead as a structure. Okay. So these are the three cases I'm going to focus on: case one, case two, and case three. As I said, the first thing I'm going to do is find out the stationary or the fixed point solutions, and these are the corresponding sort of fixed point equations. They are actually invariant, so it doesn't matter which direction you choose the z-axis. And these formidable looking expressions are the fixed point values of the order parameters. Remember what the order parameters are for the liquid crystal. It was this 2 by 2, writing things down in 2 dimensions. So for the liquid crystal, it was this 2 by 2 matrix or tensor, Q11, Q12. For this point, you have the stars, and for the next field, you have some value rho. Because it's a conserved variable, the homogeneous rho has to be the same as your initial value of rho. Then the P1 and the P2 pick up some typically non-zero value. These are the directions of the polarization. Actually, for all of the cases, you can actually explicitly solve for the fixed points. And I'm not going to sort of inflict the solution on you, but you can solve for the fixed points, and you can obtain the values of the fixed points, basically. Okay? So that's part one. The thing we do with these fixed points is you look at the linear stability around these fixed points. When you look at the linear stability, obviously you can no longer look at a homogeneous solution. You have to ask yourself about fluctuations due to these inhomogeneities. So you have to do a linear stability analysis of the complete partial differential equation. And I'm just going to sort of summarize the outcome to you in terms of these different cases. Okay. So the case one is where the liquid crystal is naturally disordered. So the temperature is above critical temperature. And the active matter is naturally ordered. So the density is above the critical density. So that's the sort of case one. And in sort of plotted the phase diagram in this region out here. So my axis is rho 0 minus rho c. Rho 0 is always above rho c, so it's always going to be positive. This is the coupling strength C0. For zero coupling, you have this guy inactive, this guy is ordered, but this guy is disordered. What happens once you include the coupling? I'm looking at some point in the phase diagram just above this bifurcation line. All of these lines, etc., are obtained analytically. And here's the sort of picture that emerges. The picture that emerges is so the first frame is that of well. So let me show you the second frame first. The second frame is that of the, which is the magnitude of the liquid crystalline order parameter. I start off with a random initial condition, and the regions where S are yellow is where you have high order, and the regions where S are green, you have low order. So as which is a random initial condition, the places of red, of green and yellow. But this field, which is now activated by the active matter, by the coupling to the active matter, actually as time goes on, develops into a state where you have rank of ordered phase moving through a background of the disordered phase, basically. Okay. So this band actually moves periodically in time. The Akash is promising that not right now. You show movies of the formation of the state. For obvious reasons, we call this a chimera. Because order in this yellow region coexists with disorder in the part of the region. So order and chaos coexist, but this is the sort of a traveling wave, so it keeps sweeping through the system in the z direction. What the order parameters of the active matter doing in this case? Here I've plotted active matter order parameters. That's the density field and that's the polarization field. So the coloration dictates the density field and it ranges from a small value to a large value. And the P arrows, which I hope you can see out here. But again, the bottom line is the following, that if field starts off random, because I had a random initial condition, and due to synchronization with this chimera state, develops a chimera state of its own, and in the chimera state, band of density is moving in the z direction, and the particles in the ordered split of it are moving perpendicular to it. Okay, so this is a chimera in our full living liquid crystal system, basically. Okay, so that's that we see in case one, and we see that in case two also, as a matter of fact. Okay, and as I said, I'll show you a movie of this soon. The next case I'm going to mention is case two, where we see other interesting nonlinear dynamic simulations. If you recall, case two was the case where the liquid crystal is naturally ordered. In the absence of coupling, it's ordered. And the active matter is disordered. And you ask yourself whether the active matter can be dragged into order by the coupling. That's the question you're asking yourself. So that's the phase diagram for this particular system. So in this case, the temperature, this is case two phase diagram. The temperature is less than the critical temperature. So the liquid crystal is naturally ordered. The density of the active matter is less than the critical density. So the active matter is naturally disordered. Okay? So I've plotted rho 0 minus rho c here, because rho 0 less than rho c, all these numbers are negative, and that's coupling strength. Okay? So let's zero coupling. You know what happens on this axis on this. The liquid crystal is naturally ordered and the active matter is naturally disordered. Now you start increasing the coupling, that state persists for a while, and you have a boundary which will obtain analytically. This boundary and this other boundary, I can answer questions if there are doubts about these boundaries. And you have interesting chimera states, and you have a soliton type state also. And what I'm going to show you next is a soliton state. Because once you get to large coupling, you just get a homogeneous ordering of the active matter of the active matter by the liquid crystal. Okay. So that's your soliton state that we observe in this system. And again, I have a movie of this also, which I hope will work. So I'm plotting here the lower set of frames are for the liquid crystal order parameter, which I called S. The magnitude of S tells you how ordered the liquid crystal is. In case two, the liquid crystal is naturally ordered, so it's not a surprise if once you turn the coupling on, it continues to be ordered. So I'm plotting here the density and homogeneity is in the field. I start off from a random initial condition somewhere out there. As time progresses, this random initial condition develops into this region here, and this region here of high density. This is moving in that direction, it collides with that, and after collision, it comes through intact, and then sort of the periodic boundary conditions keep sort of repeating that basically. Okay, so this is like a localized solitary wave, which is stable under collision, and which one usually thinks of as a soliton. Of course, soliton, there's a whole lot of machinery going with it, which some of the audience is experts in, so I won't get into that. But this is soliton solution. And the sort of interesting thing about this, it's not a one-dimensional soliton, it's actually a two-dimensional soliton. Okay? It's localized in sort of two dimensions and shows this sort of stability under collision. Okay? What is happening to the density field to the matter at the same time? The active and plotting the density, which is this blue shaded thing. So low density is blue, high density is yellow. So you develop patches of yellow, high density, yellow, high density, yellow, high density. When these arrows show the direction of the birds that are moving, And as you see, this goes through a nonlinear collision. So this is rather late in the process, this formation goes through a nonlinear collision and then emerges out intact on the other side. Okay, so the solitone in the active matter and solitone in the liquid crystal field are both synchronized in this model of living liquid crystals. How does that happen? That's right. So that's actually what I want to say. My conclusion slide, and then I'll show you the movies and take questions. So what I will talk, we formulated a Ginsburg-Landau model of living liquid crystals. Living liquid crystals are a composite of matter and liquid crystals, one passive, one active. And the physics question is, how do they interplay with each other? What is the sort of dynamics that drive into each other? Okay. So we now have a crystal, living liquid crystal model for the first time, where these two components are treated on an full footing. Okay. The second statement is the physics I built in is that the active particles align parallel to the nematic liquid crystals in our model. That's just the nature of coupling I put it. Because it's very easy to adapt that coupling so that the active matter, the birds point at an arbitrary angle to the liquid crystals. There are now experiments where there's a non-zero angle between the active matter and the liquid crystal. So that's very easily done in our modeling. And we study phase diagram and kinetics of this model. We can use standard nonlinear dynamics techniques to get the phase diagram, find out the boundaries of bifurcation and so on and so forth. We find that what is primarily interesting is what one does to the other, what one field does to the other. And we find that the ordered component can drag the ordered component into both chimeras, where order and disorder coexist, and two-dimensional kind of solitons, where you have solitary waves which are stable under collision. So that's sort of the important takeaway message. These very much like what people have seen in experiments. The experiments, as I said, are just 4-5 years old, so they still continue to be done by people. I just quickly show you movies of the chimeras and solitons. Before I sort of show you the movies, I should say that the work was done in collaboration with my colleague Varsha Banerjee at IIT Delhi and our students Aditya Vats and Pradeep Yadav. It's been submitted. We got very positive reviews and expect it to be published soon. So I think we need to close this and go to the movies. And then maybe you can just put this back on. Okay. Okay. Could you just do the chimera first? No, I guess not. Yeah. Looking at the development of the chimera from a random initial condition. Remember this blue, this green yellow thing is the matter field. Sorry, is the liquid crystal field. Where it's yellow is more ordered. And this is the active matter field, where it's yellow again is more ordered. And the arrows indicate the direction of the birds. So I started from a random initial condition, and now it's almost sort of developed into its band-like structure, a structure. And now I think it's sort of settled in. You have a band of high density moving to a background of low density. You have a band of high moving to a background of low activity. Okay, and the bands are move synchronously because of the coupling between the active matter and the liquid crystals. Can we get the soliton movie also? The solitons were the movies were made by my students. I don't know the technology to do this. Okay, so here in this case you start off with some random initial condition again. This is the crystal field. Why order is and low order are these vortices out here. These are the vortices and anti-vortices which I talked about, the defects in the field. So these defects are sort of will finally move towards each other and coalesce. The active matter is doing random stuff on its own. It's moving sort of all over the place. That pair of defects is gone. Now this pair of defects is about to collide. I hope it collides and disappears. It seems you have now a homogeneous phase, but actually you don't have a homogeneous phase. You see the emergence of these lumps of ordered liquid crystal and moving in that direction, this lump moving in that direction, and the lumps sort of collide and undergo this nonlinear collision and sort of comes to intact, and that repeats as far as we can follow it in time. Similar stuff, okay. Similar stuff if it's happening in the active matter field, the random initial condition evolves into a soliton, and the solitons are slaved is not a good word, synchronized with the solitons in the liquid crystal field. Okay. I'll stop here and take questions.
Questions?
Polarization vector is actually it is the direction of the polarization of the electron in the molecules of
Polarization vector here refers to the polarization of the active matter. So the bacteria or the birds are moving in a certain direction. That's the polarization vector, the direction they are moving in. Basically, a unit vector along the direction of motion. And if they're all synchronized, all the birds are moving together, then you have a high value of polarization. If the birds are moving randomly with respect to each other, you can just add up random vectors, and then you have a low value of the polarization.
ellipsoidal particles.
Okay, the liquid crystal is typically ellipsoidal particles. So you have all kinds of liquid crystals. I've just taken the simplest case. You typically have chalk-like particles, and there's no difference between the down states. These are called apolar liquid crystals. This is the simplest kind of liquid crystal.
Is there any check about optical property of some kind of anisotropy in optical properties?
I mean, yeah. This is a subject which, by the way, you're a young boy, so you won't know, but Indians have contributed a lot to this area. There used to be this very strong group at Raman Research Institute. They studied all kinds of properties, including optical properties.
So it seems to be tunable because
It is tunable, as a matter of fact. And actually, the switching between the isotropic state and the between the nematic and the isotropic state is what drives our liquid crystal displays. This is a 150-year-old subject, and corresponding insights have been made on this subject. Okay.
one final question. If particles can be without gain or loss, materials, molecule particles can be without gain and loss.
I didn't get your question. Just repeat it.
Gain and loss has to be there if one particular system.
See, you have to think of it from the physics angle. Okay. Let's say you have matter which is a bunch of birds. Okay. The density is obviously conserved because you're not shooting any of the birds or you're not adding more birds. So the density is conserved. So there's no gain or loss in that. But then they are pretty much free to point in any direction they want to. So that is a non-conserved variable, and on the average, you can align or you can misalign. Similarly, on the liquid crystals, density is obviously conserved. Densities are usually conserved, but the direction, the orientation is can change. It's not conserved. So the energy you have, yeah, I'm sorry, the energy is dissipated in these active matter. The energy is, so it's non-equilibrium system. The energy is dissipated.
Yeah. But speed on so I think it is better to use regular physics. Music is not right.
No, that's what I said. It's not a completely integrable Hamiltonian system in that sense of the word.
Yes.
Just curious that your you feel that your pneumatic fields seem to mimic each other. Is that always true? Because C is 0, they might.
When see, that depends on the strength of the coupling. If C0 is 0, then they just act independent of each other. So kind of coupling I've shown you results for, I have made experiments where they deploy parallel to each other. But the dynamic steel need not be, it could be out of phase or something.
Is there should be some.
We are investigating that as a matter of fact, yeah. But partly it's due to the coupling that they are synchronized so nicely. Yeah.
But I'm wondering if it's also.
Yeah. But the dynamics need not be synchronized. Yeah. Uh, yeah.
She, your state is the very acidity breaking state. Acidity is problem.
The density has this inhomogeneity. And let me actually raise that question. So the density has this inhomogeneity. So it's like a liquid gas transition basically. You have coexisting liquid and gas states. You have regions of high density and you have regions of low density basically. So that's so if you want to speak in a symmetry breaking language, or if you look at the order parameter of the liquid crystal, you have highly aligned nematic states here, and you in the green regions are the isotropic states. So you have coexisting isotropic and nematic states in the same system.
The other is
Yeah, she's got a question for one. Yeah.
This one concept. This one seems nine with the shutters are in this place, which need to. Okay.
Okay, so this we are referring to the liquid crystal being ordered and the active matter being disordered. So you can think of it as like ordering of the liquid crystal drags the active matter into order. It would like to be intrinsically disordered, but the coupling drags it into order. Usually the disordered one is dragged by the ordered component. That's why I said the case where both of them are disordered is not of interest because the coupling will not really do very much to you in that case. Okay.
Because so straight away both are comparable. But then we said comparable, which one we use that thing? Comparable say.
See, one of the order parameters is naturally ordered and one is naturally disordered in all these cases, basically. So now it's a question of how much the coupling strength is. If the coupling is very weak, you're not going to drag one into the other phase. Huh? But if it's sufficiently strong, you get chimeras, where you get coexisting order and disorder. And if it's very strong, then you get full order because of the coupling. That's the sort of way to think of it.
that's good. For static and cholesteric liquid crystals.
Right. Yeah. Let's stick to the simple example right now. Okay. Yeah. There are all sorts of liquid crystals, and I mean, I don't know whether the experiments done on those. Yeah. Or for living liquid crystals, whether they are experiments. The liquid crystal part of it is well studied. But yeah, they're not the living liquid crystal experiments are done on nematic liquid crystals. Okay.
That's so now what's the meaning?
No, please, that's the most interesting question. Okay.
Yeah, so this how we plan was talk later. And just yeah.
it's fine. We can realize. So, what I will talk about is essentially about instabilities and how data comes in from thinking about instabilities and so on. So, instability, of course, the first thing that comes to mind is Lyapunov exponents. I guess the first lecture in the nonlinear dynamics class, maybe. And what I will talk about is how to characterize instabilities more precisely using what are called Lyapunov vectors. They don't appear anywhere on the slide, unfortunately. Anyway, so that's the beyond Lyapunov exponents. How do you characterize instabilities using Lyapunov vectors? That will be the main focus. And why are they important? How they get used in thinking about data solution problems, how instabilities and uncertainty in dynamical systems are related to each other. And then how do you compute the Lyapunov vectors? Using actually the data attributes. So that will be the main focus, which is some of the results. And unfortunately, it turns out that Lyapunov, unlike Lyapunov exponents, which are quite stable in the sense that there are different ways to compute Lyapunov exponents, and Lyapunov exponents are quite robust in some sense. Lyapunov vectors are not. Unfortunately, that's what it looks like, and so we like to explore further what it is. That's clear there. So now first we're starting with pictures, and we'll start with equations, and the equations are important and not just the equations. Essentially, if you have this is probably maybe a couple of weeks of nonlinear dynamics class in one slide, one line, which is that associated to every nonlinear equation, there is a corresponding linearized equation, and the dynamics of the linearization leads you to Lyapunov exponents, and as we will see, also the Lyapunov vectors. So, and this is essentially obtained by taking the Jacobian of the nonlinear function that defines the nonlinear system. So that's, let's say, very basic fact of linear dynamics, and the dynamics of this is linear. As you can see, Q appears as a linear term. Of course, it's non-linearly dependent on X, but and so the solution of this linearized equation, it can be written simply in terms of matrix propagator, and the matrix propagator is what is used to define the Lyapunov exponents. I'm not quite sure if that is done this way in many physics classes. It's usually you start with something like this. Heuristically, you take two nearby initial conditions and they diverge exponentially. That's E lambda t for lambda positive, and that is an indication of instability in the system. This is slightly more than that in the sense that you do not think of fixed points or trajectories nearby, but rather you are basically thinking of solutions of the linearized equation, which more precisely captures this exponential divergence or convergence if that makes sense. And so that takes us to the definition of the Lyapunov exponent, which is that as you go forward in time, so t goes to infinity or t goes to negative infinity, you look at how the linearized was decays in time compared to what its initial condition was in logarithmic scale. So if you simply forget this limit that appears here, you take this on the other side, this is saying that mz is e to the power lambda z. So that these two are essentially this is a heuristic explanation of these pieces of definition. So forward time and backward time Lyapunov exponents need not be the same. So and in particular, they not necessarily the case for solutions. So I put that definition again here. They depend on two things. One, they depend on the initial condition of the linearized equation. So different, but just to do that, it's here. So this is a vector. This is the tangent vector to the trajectory. The tangent space has the same dimension as the phase space itself. And so if you have, let's say, three-dimensional system, there are three vectors in the tangent space, and each of the three vectors will have a different potentially, they could have different Lyapunov associated. So it depends on the vector that you choose to solve the Newton's equation. It also depends on the time, the base point of the phase space. So this depends on the initial condition, and essentially it depends on time through this initial condition that we start with. And so each phase space point will have a different, potentially, will have a different Lyapunov exponent. Okay, so because of harmonic theorem and so on and so forth, that we can talk later, that doesn't happen. The Lyapunov exponent happen actually turn out to be the same for all phase space points. That's part of also the Rich theorem. But in principle, they can depend on both the initial condition of the vector and that time. That's what happens. So in general, there is a spectrum of Lyapunov exponents. So n-dimensional system has n Lyapunov exponents in general. Up to n Lyapunov exponents. And for many practical systems, Lorentz, Rossler, this and that, and so on, they are actually n Lyapunov, so it doesn't equal to n. So they really n Lyapunov exponents in the n-dimensional system. And typically, so lambda 1 greater than 0, the larger Lyapunov exponent being positive indicates chaos. Okay. So, of course, for a generic initial condition of Z, this will the largest Lyapunov exponent dominates. So that's basically what you see in practice. If you just try to solve this equation, you get growth at the rate of the largest Lyapunov exponent. That's basically because of this. You can think about this. So a generic initial condition grows like this. So what initial condition will give you, let's say, specifically the ith Lyapunov exponent, not the largest Lyapunov exponent? And heuristically, again, that is exactly the ith Lyapunov. So there is corresponding to the spectrum of Lyapunov exponent, there is a set of Lyapunov vectors which grow exactly at the rate of each of these, at the rate given by each of these Lyapunov exponents. And so effectively you can think of it as if there are n Lyapunov exponent, there will be n vectors, and they could form a basis. For example, in general, they do form a basis of the n-dimensional vector space, and those n vectors grow at the rate of these n Lyapunov. Okay. So it and they are basically ordered in sequence. They give you subspaces defined by the fact that when you are in one subspace, you don't have a projection in the other one, when the growth rate is given by that. So that's the basic picture of what Lyapunov vectors are. Let me, sorry, apologies now. I will jump a few slides and this later. And so for a fixed point of the autonomous system, just to get some intuition about what these Lyapunov exponents are. For a fixed point of the autonomous system, the Lyapunov vectors are simply the neutral, stable, and unstable spaces of linearization around a fixed point. So that's the simplest case where you can simply calculate the Lyapunov vectors that have linearity. A slightly non-trivial example, just you can think of these are actually, I'm cheating. This is really, it's not good cheating. What is this? There are essentially n uncoupled linear equations, except that they are non-autonomous. So it's simply x not equal to x, but A is time dependent. So non-autonomous systems. And unlike most other talks, I give you homework, which is calculate the Lyapunov exponents and Lyapunov vectors for this problem. It's straightforward to do, but non-trivial in the sense that you will have to well, this is an example where the forward time and backward time Lyapunov exponents are actually not the same. So these two are in same. For example, for non-autonomous systems like say the climate, which is this thing. Okay. They have been studied for the last maybe 10, 15 years, 20 years extensively. The definitions go back close to 100 years. There were no good numerical methods to compute them, hence they were not very useful in practice with large dimensional, actually even small dimensional problems. And these have been developed in last maybe 10, 15 years, and so now used extensively to understand the dynamics, the more detailed version of how to understand instabilities. They come up in studying extreme events, critical transitions, and so on and so forth. I'm not going to discuss those because my focus is on how to compute them using data. Okay, so just to another illustration about how they look like for say the most favorite model of nonlinear dynamics, which is Lorentz model. And first, so there are three diagonal vectors for Lorentz equations because there are three dimensions. And in the first diagonal vector projected in the x, or sorry, x z. And you can see there is a complex structure of these diagonal vectors depending on where in the phase space point you are. It's something similar for second one. Yes, so the angle between these two vectors. They sometimes, and this is what gets used in practice. So this angle actually is the cosine of the angle between -1 and 1. So angle between was 0 pi, and the angle is shown here. So you can see that when trajectory is on inside and low, things are either between -1 and pi, and the transition period is when you get what is the interpretation to these that can be used? So that's just an introduction to the vectors. There is a bit of technical detail which I covered here. That as I said, there are possibly different forward and backward diagonal exponents. In practice, that doesn't happen for say Lorentz systems, but for diagonal vectors, that's actually not the case at all. So the forward diagonal vectors and backward diagonal vectors are typically different. In general, they are different. Generically, they are different. And so the forward ones are the ones with the exponent lambda plus going forward in time. The vector that leads to the exponent plus. So even if lambda plus and lambda minus are different, the forward and backward vectors actually have different relations. So sorry, even if they're the same, even if lambda plus and lambda minus are equal, the vectors will be different. One vector will take you to plus. Similar vector will take you to the same value lambda plus, but the vector is boosted. So those are forward and backward. They do form orthonormal bases. So there will definitely we have to deal with these two vectors. So the covariant diagonal vectors, which is effectively the intersection of these two subspaces, give you the type of vectors for which both forward and backward time diagonal exponents are the same. Sorry, are lambda plus and lambda. So if you have just the same set of exponents, then the covariant diagonal vectors are usually useful in practice because it doesn't matter whether you're looking at backward or forward in time dynamics. And this is critically important as I will come. Okay, so they have other properties like they map to the linear vector and so on. So they have desirable properties that they use in practice as well. Bunch things is here and all the important things. So why instability is important because many of the systems that you encounter in practice are in fact unstable. So the example that's given is a very extreme simplified version of some kind of atmospheric model. Everything else. So here the engineering is as follows that every trajectory of course looks alike in the sense that there is harmonicity. But if you are dealing with a single specific system, then the trajectories that you are interested in may diverge from the trajectory you are trying to compute, for example. So trajectories, nearby trajectories diverge from each other, but statistically, asymptotically, they look alike in the sense of averages over that particular same. So these two are interesting properties, because of which two things happen. If you want to study a specific trajectory, you need the data about that specific trajectory. But on top of it, because of the fact that the statistical nature is similar, you need probabilistic description of the problems. So those two are necessary. It automatically is necessary because of the chaotic nature of the system. So, let's skip this about deterministic versus probabilistic predictions. I say the point is that you always have to deal with probabilistic predictions. So how do you converge? How much time do I have? How much time do I have? 10 minutes. Okay. So essentially, how do you incorporate data sets? The way a common way to do this is to Bayesian techniques. So if you have a model, I'm going to describe this in discrete time because it's much easier to describe in discrete terms than in continuous terms. So if you have a discrete line dynamical system, or think of it as a discretization of a continuous time system, and there are some observations that you have. The observations are noisy. This itself could be possibly noisy and that's only hard condition to get. But if you have a model and some observations of the two, the problem of nonlinear filtering essentially is a statement of how do you incorporate the observations into making estimates of the state of the system. So what we want to understand are the estimates of the state. So let's say we want to get estimates of the state at time 1 through n using observations over that time. And that's the problem of nonlinear filtering. And effectively, it is the conditional probability distribution of the state conditioned on the observation that is the object of interest. So you take all the observations, find the conditional distribution of the state conditional observations. So as I said, we go from describing dynamical systems in terms of trajectories to describing them in terms of probability distributions. And in this case now, what we are interested in will be this conditional distribution of the state as a function of time. And in particular, what happens as you move forward in time. So there is also aspect of instability for this problem, which is that is this distribution, does this have some kind of stability properties associated with that? So for that I will skip that. But essentially the question is identical, which is if you start with two different probability distributions as initial conditions for this for this forward evolution, do they eventually go forward in time and become similar distributions of output? That's a question that we that's effectively called the stability of the filter or stability of the data selection problem. And I think I will completely skip this altogether. Okay, so maybe just mention one thing that is important, which is right. So these filtering distributions, what's making it back to the upper filters, is under certain conditions we can prove that they are actually stable, and in addition to stability, they become degenerate distributions, and in particular, they are actually they concentrate on the unstable directions, which are given by the unstable Lyapunov vectors of the dynamics. So the probability distributions relate to the Lyapunov vectors, but naturally. And this is why also knowing the Lyapunov vectors is important, because then it tells you about uncertainty as quantified by this conditional probability distributions for the system. So back to Lyapunov vectors. How do you compute these Lyapunov vectors using data? That's a natural question. There is a sort of not fairly well established algorithm for computing these vectors if you have the model and the linear distribution of model available. And this is a picture of it. You start with some initial condition, you go forward in time, solving the linear distribution. And then there is a backwards equation, which I will explain just one. So there is a forward equation. Once you go forward in time, you can see that because there are positive and negative level of exponent generically, some directions will grow exponentially, some directions will contract exponentially, and these matrices become quite similar very basically they get very hard very quickly. And after a little bit of time, you to a normal organization using, for example, CQR decomposition, because they keep the subspaces, the unstable and stable subspaces the same. CQR decomposition gives you the orthogonalization of the subspaces made by the matrix Q. And the matrix R in the QR decomposition can give you the stretching and the contraction of the directions of these vectors. And so you basically store the stretching and contraction components as well as the components of this matrix Q. This is going forward in time, so that gives you how different vectors grow or contract forward in time. And these steps, so you go, let's say, from time ta to tb, and then from tb to tc. So that gives you the backward diagonal vectors over that time interval. And you take the same steps coming time, and they give you the forward diagonal vectors at the beginning time. So why does this forward iteration give backward vectors and the backward iteration give forward vectors? That's part of the homework. Think about it over and then, because once you have the forward vectors and the backward vectors going forward in time and this backward in time, the intersection of these subspaces essentially have the invariant diagonal. That's the standard method. Now the question is, you need a trajectory completely and the linearization around it. So what do you do if you don't have the complete trajectory? So if you only have partial observations of a system, one way to do it would be that you use one of the many different possible methods that you may have learned about of constructing the approximate dynamics from the observations. So you use something like time-delay embedding methods, or what are now called DMD methods, and so on and so forth, to reconstruct the dynamics and use that to compute the approximate. This is what is done in this but in addition, if we do have a model, we simply don't have a trajectory around which we want the covariant abnormalities. If you do have a model, what do you do? Well, one way to do this would be to use this data assimilation. We don't talk about algorithms to implement data assimilation, but we can use this to get estimates of the trajectory using the probability distribution that I'm talking about. The conditional probability of the trajectory conditioned on the observations can be used to then compute this kind of models. And that's what we have been working on for last maybe year or two or so with my student Shashank Roy. And this is what the present, the results of this is what I will create. Okay, so the exact level of vectors that I will talk about essentially are the ones that you obtain from just going forward in time. And the approximate ones are the ones that are obtained from these data simulated approximate trajectories. 3 minutes? Yeah. Oh, there are 2 chairs now, sorry. Well, you are the chair, you be over and then we can also do. So, so the approximate ones are the ones that we completed using this data simulated trajectories, the exact ones. These are all numerical experiments. It's not done for something like climate change or experimental data. But and so we compare these exact and approximate ones and try to understand how sensitive we are. Okay, so this is the picture that I showed earlier, which is the cosine of the angle between two covariant diagonal vectors for the exact computation, exactly numerically as exact as possible computation of these covariant diagonal vectors. We do the same thing for the simulated, the data simulated trajectories. This is the features. Of course, you can see that the trajectory itself is now noisy because this is the estimate of the true trajectory, and as a mean of the probability distribution which I talked about. And you can see that generally, sort of the overall picture looks kind of similar. And this is the three-dimensional system, 63. Things become quite significantly bad when you go to high dimensions. Okay, so this is just a picture of the cosine. Oh, actually, the angle itself, and for really large perturbations of the order of 29. So you still have angles which are of the order of 5 to 10 degrees, which is reasonable approximation between 5 to 10 degrees, which is not bad. Just obtained using data. Okay, so but when you go to high dimensions, this becomes much worse. So say 40-dimensional model, it's called the 1x26 model. And this 40-dimensional model, I'm showing the 40. So this index is the index for the diagonal vector. And this is the angle between the true and the approximate diagonal vector that was computed using data. So you can see that when even with for all of these vectors, the smallest angle is around 10 degrees or so. And anything beyond 30 or 40 is pretty useless because you want to find a unit vector. If you have an accurate only up to 30 degrees, it's not such a great approximation at all. So using these vectors, it's extremely sensitive and difficult to get a good approximation of the true diagonal vector. That's essentially the conclusion of this. What you can get are the auxiliary subspaces, and I will not talk about the subspaces because of lack of time, so it's going to make you very uneasy. And if you have questions about this, you can ask me later. Well, these are not random. So if you have random, here's a homework problem again. But take an little n-dimensional subspace in a capital n-dimensional vector space and find the angle between a ith dimensional subspace of that n-dimensional space randomly. So take a random ith dimensional subspace. Two random ith dimensional subspaces and find the angle between those. What is the answer? So here is the answer then. And this is completely not random clause. There is information in these subspaces, but they are simply not accurate enough by per component wise, they are not accurate, but subspace wise, there is a lot of information that you can get. You can get subspaces even up to say 9 or 10 dimensions. This is so that edge subspaces are not the other. Okay. I guess that's the conclusion. So I'll stop here. The details you can read. Thank you.
You have time for a few questions, maybe? Yes.
It's fine. You have a differential equation governed the system. And you can compute the jet derivatives and the again vectors of the jet industries that able to produce. What is the relationship between those vectors?
Sorry, it is in the sense that it's a whole integrated quantum. So point wise, there is no relation. Except for the fixed point.
Any other questions? So let's thank our speaker again.
Winner from the okay.
Okay. Our next speaker is Professor M.S. Sultan from ISF Pune again. Please.
So first of all, let me thank Shyam for Square Conference for inviting me as conference. And I'm not going to explain that. We'll see it as we go along. Maybe when you get your question on this later, something like effect of chaos in the interactions of the organization. Which begs the question, what is least for making decisions? And I think already says they are go back and percentage from
chaotic systems. Already Sudeshna said like stadium billiards are one of those classic chaotic systems. And here it is. So it's basically a single particle, the dynamics of a single particle inside a potential ring. So it's a single particle, but bounded by a potential which looks like a stadium. So every time it encounters the boundary of the stadium, there is a specular reflection. It's a very simple enough system. And turns out the Indian chaotic system, basically chaotic systems. If you go ahead and quantize the system, different its eigenvalues and eigenfunctions of the system, what you see is that most of the eigenfunctions of the system look like this. Typical delocalized things. Every now and then, you will see things. So you see that there are these enhancements and properties that is in size growth. So there are these unusual enhancements that you will see occasionally in some states of the system. And if you take the overlap of the wave function with some basis state, I mean, just plot it out. Number, what you will see for a delocalized state is that it essentially populates the entire basis state. On the other hand, for a localized state, you will see such strong enhancements only at certain basis positions. And these are not figments of mathematical imagination. The experiments have been done. So this is one of those realizations in a microwave system. So this is an example. And these kinds of, so in fact, this particular picture, see this dark line here. This corresponds to a classical periodic orbit, and quantum probability density has essentially concentrated around that period. So indeed, these are actually called the bouncing ball orbits in the stadium case. So there is a whole theory behind it. It's called stars and it's associated with unstable periodic orbits with these kinds of so that, but essentially the point is that consider that this genre of localization, the localization arises from the fact that you have certain invariant structures in classical phase space. So in this case, it is a periodic orbit, and that gives rise to quickly quantum. On the other hand, there is an entirely different class of localization, which is called Anderson localization, which arises for very different reasons. This is a classic chronic penny model kind of problem on studies in textbooks. You take a periodic potential, send a wave packet, you get block solutions, block waves. On the other hand, if you had a periodic potential, but the on-site potential is random, like shown in the figure, you will end up with a localized. You will end up with a localized solution. So in a three-dimensional system, you would, for very strong disorder, you will have localization. If your disorder isn't sufficiently strong enough, you will end up with something that is distorted and more localized. Once again, this is a classic case of Anderson localization arising from destructive quantum interferences. So this is what you would say is a pure quantum localization. Supposed to the previous case, which was essentially in some sense a reflection of what has happened in the classical region. And this is a picture from the paper in 2008. This is Anderson localization of matter waves. It's an experimental. So what telltale sign of Anderson localization is the exponential profile of the eigenspace. Irrespective of how you begin with, one of the signatures is that the localized state has this exponential profile, which will look like this from looking at it in the position space. Some form like this, where this is the localization. And indeed, one comes across this in several models of quantum chaos. Peak total is one of them. I'm going to say what the model itself is in a few moments. But you can see that these are those exponentially localized. This is in the experiment. This is a numerical. these look straight lines because the loops are being taken on. Yes. This to distinguish this brand of localization from the Anderson localization, this is given the name dynamical localization because here in this case the localization emerges due to dynamics as a function of time rather than as a function of a current. And in the case of kick total, this typically happens in the momentum space. So your exponential profile is actually e power minus p divided by typical localization. Okay.
So once the singularity at x equal to 0 or p equal to 0 is the simple way to understand. I mean, the function is singular, right? It's not analytic.
It's not analytic, yeah. That's one way of seeing it, I guess. Yeah.
Well, actually, is this a simple way to understand why it's. I mean, I would normally expect it to be continued, sort of analytic. Maybe, yeah.
Okay, I can think about it. I don't have an immediate answer for this. Yeah. Okay, so this is one slider on what chaos is. So suppose typically we look at systems like this, Hamiltonian is just split into a integral part given by H0 and there is some potential and this is the chaos parameter. So that as you tune this parameter alpha, you essentially get into a chaos regime classically. So typically when H0, when alpha is 0, your phase space will be dominated by invariant torics, so you get nice looking curves like this. And of course, there are, so when you say something is integrable, it goes and if you are in an interdimensional system, there will be n constants of motion and so on. And if for is sufficiently large, you end up with something like a random collection of points. And in general, this is one way of figuring out chaos. Typically, most of the time, we can't calculate things like Lyapunov experiments. In fact, this is easier way. The other way is you do all the normal programs that Amit had given, understand Lyapunov experiments, calculate Lyapunov experiments, and figure out. Okay, that's what this picture is. Okay. And kick total is a simple system. Uh, so essentially, it's a free particle which is periodically decayed. So you can think of this in two ways. One is suppose let's say this series of delta functions is action. It's simply a pendulum problem. So you can think of it as a pendulum which is periodically kicked. So in other words, you have a pendulum for which you are giving energy periodically every hours. The other way to think about it is very useful for our purposes is this like suppose this is my time axis, but every integer time has there are these kicks that is important and kicks are of this form k sine k cosines. And you have a particle which is essentially negotiating this space. And that's another way of thinking about it. A particle which is by and large is most of the time executing free dynamics, but now and then periodically is experiencing a product of a process. So this is a chaotic system, fairly simple enough, and can be reduced to a differential equation or and when you this is the parameter that you need to keep in mind as you increase the strength of this kick, you go from what looks like integral to chaos dynamics, and this is fairly well understood in terms of polynomial one was a scenario. So you break away from invariant curve and end up with okay. If you if you do the quantum dynamics of the system, since it is periodic, you have those series of delta functions, periodic kicks. The natural way of putting it is in terms of this Flaque operator. And now all you need to do is just initial state and just apply the Flaque operator in times. Then you get interesting thing is, if you look at the classical energy, it increases in an unbounded way. So, I mean, this is something you should expect because, after all, you have a particle and you're going to impart, you're giving energy externally to it continuously, and the particle is simply absorbing that energy. So, the energy of the particle basically keeps it. On the other hand, quantum mechanically, you're doing the same thing. You're still giving it energy periodically. On the other hand, it shrinks as only for a very short time. It will follow the classical dynamics up to what is called Einstein's time scale. Such phase. So after this, there is no increase in energy. The system refuses to take in the energy that you are giving. And this has been like experimentally realized in four lattices way back in analysis. The interesting thing about this is that this system quantum controller can be actually transformed through a nonlinear transformation to the Anderson model or to something that looks like an Anderson one. So you will have all the upstream term and translate energies and so in that sense, what you have is Anderson model on one hand, and you have the quantum kick proton on the other hand, and you can actually say that they are essentially different parts of the same phenomenon. So all the empty states of the Fouquet operator are exponentially localized to momentum space. So the rest of the talk, what I'm going to do is to use this localized states and do something with it. So one can do whole lot of things with these localized states. For instance, it's a very useful template to study metal insulator transition. It's very hard to study Anderson transition in real solids. But here you can control everything and actually do that. And it has been even experimentally realized. In fact, you don't need to do a three-dimensional quantum computer. The way of doing it even with one-dimensional quantum gates in a quasi period. And you can also realize quantum analysis to understand coherence mechanism because this is one of the systems which use to clear signatures about the classical limit and the quantum limit. They are completely different. So if you are interested in studying how you approach from quantum to classical limit, this is one of those nice toy models to work. Okay, we're going to basically discuss results from these three, and which kind of time I have, I will be happy if I can even go to the first and second. Okay. So this is the work that we have done a few years back. So just to recall, if you give periodic kicks, that's the kick product scenario. You give periodic kicks, you get dynamic progress. That is this curve, this blue curve in the schematic. But on the other hand, if you do aperiodic kicks, what happens to it? So the general, what is known is that till 2017 or so is that if you give any kind of noise in the quantum kick rotor, you can put noise in many ways. For instance, one of the ways is that these are the integer times when the periodic kicks are occurring. But on the other hand, you slightly displace it. And the time difference between this black and orange curve here will be taken from some distribution. Let's say you're giving it a stationary noise. So in such case, what would happen is this localization is more or less immediately lost, and the quantum mean energy will follow the classical mean energy curve. So essentially, you have induced a decoherence. But on the other hand, suppose instead of taking this to be a stationary noise, if I take it to be a Levy distributed noise, a non-stationary noise, then something different happens. So let me just explain to this picture. So what I have here is the usual periodic. So this is the time axis here, and underneath the lines that you see are where the kicks are starting. So lowermost is the case of periodic kicks. And what I'm doing is that I'm missing kicks. And this distribution is essentially something like this, and then there is this parameter alpha. We call it Levy parameter. This parameter alpha determines how much kicks are being struck. So essentially, you're fiddling with the coherences being built up in the quantum system. And it so you should typically, going by your previous intuition, expect that the dynamic localization should have been lost. And so this entire scenario of kicking with these waiting times taking from a taken from the levy can be implemented for very simple change to a hammer to devices. So we can go through the calculations analytically, but what I want to point out is that in this case, please show the result. This is in a sense exactly not exactly solve a problem, but at least approximately can be analytically solved. In fact, every quantity, including the decodance, can be analytically obtained. So you see here are three things. So in this term, you have um, the analytical result, the experimental result, and the numerical result. So the experimental results are the dots that you see, and analytical result is the dotted line, and the numerical result is continuous. So as you change, modulate your value of alpha, simply when the value of alpha is less than 1, the coherence time essentially diverges, and the native test here coherence leaves uncontrolled. So you are able to control the progression to the classical line. So this black line that you see here is what you would expect whenever you restore your phase coherences. However, turns out that if you use this very kick scenario, you can actually control this kicking. So that is one kind of result. And so next, I'll talk about what happens to localization in the presence of interactions. So till now, all we had was a simple model with a single particle in a nonlinear potential. But what if you had two kick rotors which are interacting, or many kick rotors which are interacting with one another? How does the result change? In particular, will there be localization or not? Okay, so this is the model that I have. So it looks very similar to the standard kick rotor that you saw, except that its V of theta now has this additional part, which is the interaction. And you can actually use either the nearest neighbor interactions, or you can, have a more meaningful interactions and so on. And one here. So is the two important parameters that we track is this, which is the strength of interaction nodes, and of course the kick strength, so which we have been using from earlier. And n is the number of nodes. And now, before we see any results, we just have to first ask the question: why do we need to even study a collection of kick rotor models? Well, if one kick rotor is chaotic, your intuition might tell you that sitting many more is not going to show you anything different. Okay, so the question of interest here is dynamical localization sustained in the presence of interactions. So when you have many of them, they interact together. Is that still dynamic localization, or are you going to lose? And what is the fate of dynamic localization in the thermodynamic unit? So when you take the number of kick rotors to infinity, does it still survive? And are you creating any new dynamical phases? So in the earlier case, we had only two phases. In one dimension, you directly went into a localized phase. There was some time for which you had a quantum diffusive phase. Now, question is, beyond these two phases, quantum diffusive and localized phase, is there anything new? Let me give you the answer first. So the answer is that dynamical localization indeed persists when you put together a finite number of tests. And as far as thermodynamic limit is concerned, somehow the results are not all. So in general, there are several papers which say that you lose all semblance of localization when you go to the thermodynamic limit, but there are at least two important systems which are counter examples, which do show dynamic localization even in the thermodynamic limit. So I think the last word on that question is not it. What about the new dynamical phases? Is one new dynamical phase that we see is a subdiffusive phase, which we don't see in the standard kick rotor. In Hamiltonian chaos, you will never ever see a diffusive phase density. So this is something that happens pure quantum phenomena. So these are questions of broad interest, not just in quantum chaos, but in the entire advanced matter physics. So there's a whole lot of literature on interacting spin chains and stuff like that, where they worry about whether there's localization or thermalization in the thermodynamic and so. And as I said, think floaters are again very useful to study simply because they display very different characteristics in the class. And also more importantly, there is a very definite classical limit. Like spin chains, many times you need to infer the so-called quote unquote classical limit from what happens through random matrix theory and so on. But here you do have a classical limit. You can use the equation of motion so that and figure out what. Okay, so let me give you two quick results. This is for the case of n equal to 2. So there are just two quick rotors which are interacting with one another. And this is the work of motor making. Here, this plotter is this phase of phases. On the y-axis, you have the interaction strength, and on the x-axis, you have heat strength. Those are the two interactions that we have to write. And what do you see here? So you do see a large area where there is dynamical localization, and you also see a large region of where it is dynamically delocating, or where you can expect to see quantum diffusion. But in between the transition from localized to delocalized, you also see a diffusion region. Okay, so here, when you say that it's localized, delocalized, or subdiffusive, it's more easier to track them in terms of how the energy evolves as a function of time. So, for instance, when it is localized, energy goes as t power 0. In other words, it's basically a constant. So, if you think of this as t power beta, the beta is 0. And here in the subdiffusive regime, beta will be any number from 0 to 1. And so here it goes as t, so beta is 1. So we are going to keep track of these values of beta and from that infer about various phases. And this is another view of basically the same result, but this uses some of the random metrics. So I'm not for want of time, I'm not getting into that. So then one thing about this the kick plotter model, if you remove the interactions, the filter is still there. So you had two interacting kick plotters, and if you remove the interaction, the interaction is still there. So we want something which would have an interlevel element. So we looked at what is called this linear kick plotter model. It was introduced by Michael Berry in 1984. Actually, even earlier than that. So this is basically a particle which is a free particle on a ring, and 2 pi alpha is the speed of the. But otherwise, it looks very similar. So the first thing about this interesting model is that despite the kicks and has a visual similarity to keep this is actually an integrable system. Absolutely no chaos in this model, in the linear kick plotter. And secondly, not only in a single linear kick plotter, you can put together any number of linear kick plotters, embodied kick plotters, and you can take any interaction in position space. And that is still an integrable system. So, in this interacting system, dynamic localization persists well into the thermodynamic theory. We wanted chaos. So what we did is to replace the interaction in the position space by interaction in the momentum space. So we'll keep track of two parameters, Kp and Kp is the interaction strength and K is the kick strength as usual. And so again, it is still two kick protons Now, the system is very simple enough that you can actually calculate the Lyapunov exponent nearly easy. And so this is the full various phases of the system. So this region one that you see here, maybe I'll go to the. So you can look at this figure, but we go back. It's basically the same figure here. So the region one that you see here corresponds to the region where the system is completely integrated. For the choices of K and Kp, kick strength and interaction strength. And here, so this is your classical dynamics. Obviously, the energy has saturated mean energy. The quantum mean energy also saturates. So here you do see localization, but it's a kind of localization which is influenced simply by the fact that there are classical invariant structures because of the integrability of. So that is what this kind of localization comes from. So this is the localization due to semi-classical effects. So now we look at region 2 here. So in this case, this is actually the region where you see a true dynamical localization simply because classically the mean energy simply increases linearly with time. So you see here, quantum mechanically it saturates. Uh, uh, dynamical localization regime. And this third region that you see here is quantum subdiffusion. And here, again, you see that the mean classical energy increases linearly, but the quantum energy is on the sublinear. So that's your subdiffusive regime. And finally, the fourth regime is where both of them increase linear. So this is the true quantum diffusive phase. So this is a model where you can remove the interactions and you will have a integrable limit. And you can see not just the subdiffusive phase, quantum diffusive phase. You can also see a localized phase which is influenced by the classical. Okay. I think I shouldn't test the ratios. So I think I'll just take less than a minute to say that. So here, the interesting thing that you can actually that you can realize quantum vectors, which is in some sense an equivalence of well-known thermal matches which have been studied in statistical physics for a very long time. So typically to realize latches, you need to break special temporal symmetries. So with the localized expecting system, what we do so exactly here is that just the fact that you have a localized system, sorry, just the fact that you have a interacting system intrinsically breaks the temporal symmetry. And now you can use that to generate the ratchet currents at the subsystem level. So in fact, if you think of it as like two kick rotors and this is your interaction potential, that's your full composite system. And the full composite system preserves the spatial temporal symmetry, there can't be directed currents. But on the other hand, the fact that you have interaction potentials induces temporal symmetry breaking, can actually realize directed currents, but at the subsystem level. So I think that's a summary, but it's a longer story for another day. I think I'll just summarize. So chaotic quantum systems support localized states. In 2023, this can be a result. This is very well known for the last 50 years. And so you can engineer localized and diffusive phases by manipulating kick sequences. You can control decoherences, which is what I tried to show. And in interacting quantum system display a variety of lucky phases, localized, diffusive, and whatnot. And dynamical localization first is finite number of rotors, but we still do not know what happens in the thermodynamic limit, and it has many other applications which is probably not to be taken up. No? And so I should acknowledge the students who had worked with me on this. So Shankupal, Bharati Kannan, who is here, and Anjali, all three students. And much of the experimental work In fact, every experimental work was done by Umakant Kapol and his students. So these are the two students who led the experiments. So most of the results I presented are there in our recent physics report article with much more of a more general perspective of the field. I think that's enough for reason. Thank you for your attention.
Time for a couple of questions, maybe. Questions from the audience?
Yeah, please. Yeah. Okay, so that's based on this beta. So okay, I maybe I forgot to say. So this the current code is basically reflects the yeah, that's right. So whenever beta changes, we track the contour of where the beta changes from, say, zero. For example, so here, so this line, for example, is corresponding to this way, where KAP is equal to 1. Because that separates the integrables from KR. And these are simply based on the values of beta.
Any other questions? Yeah, please.
So it is a continuous function. It's not as sharp as this figure makes it out. Yeah, it is not. Yeah.
Last question. Not that Sega speaker yet?